Have you ever looked at the Earth from above? From so far away that the continents blur into color and the clouds curl like quiet brushstrokes over blue. It looks still, almost timeless, but time is never still. Not for this planet. The ground beneath our feet is a restless traveler, and tonight, we are not staying in the present. Tonight, we're going backwards not by decades or centuries, but through the unfathomable depths of time itself. We are slipping beyond the grasp of history and deep into prehistory, back to a version of Earth that no human has ever seen. The spinning slows. Cities blink out like embers in the wind. Coastlines unravel. Mountains dissolve. Rivers dry and retreat into ancient scars in the stone. Forests shrink into patches, then vanish altogether. Ice sheets peel back. Deserts bloom in reverse. The oceans grow deeper and darker as coral reefs collapse into calcium dust. Tectonic plates begin to rearrange, rewinding across the surface like drifting puzzle pieces. As we rise higher, the familiar shape of the modern Earth contorts. Africa swings to the east. South America detaches and slides toward the tip of what will one day be Antarctica. India, still a wandering landmass, creeps away from the southern supercontinent. The Atlantic Ocean narrows, its basin closing slowly like a breathing lung at rest. The Pacific stretches, then bends, its borders no longer lined with the sharp edges of modern coastlines, and with each passing second, we lose millions of years. We're past the Ice Age. The mammoths disappear. The great savannas of Africa roll back into jungle. Deserts shrink. The forests of Europe thicken. The Himalayas, still rising, begin to crumble down. We're past the dinosaurs, now past the asteroid, past the flowering plants, past the warm, shallow seas of the Cretaceous. We move faster still, until even the dinosaurs are unborn, their bones still locked in possibility. We're now reaching a time few imagine. 500 million years ago, a time before anything we would call normal. The Earth looks alien. Not just the surface, but the very skin of the world breathes differently. The air is heavier. The colors are off. It's still our home, but it isn't ours. From orbit, the continents are unrecognizable. What land exists is mostly gathered in clumps in the southern hemisphere, sprawling masses shaped like broken shields. Towering mountains are rare. Most of the terrain is low and flat, weathered by billions of years of wind and water. The oceans dominate, deep and boundless, covering over 80% of the globe. There are no polar ice caps. The poles are warm. The planet tilts differently, and its rotation is faster. Days are shorter. Years are longer. The surface is quiet, but alive. Life is primitive, mostly underwater, and the water thick with ancient minerals shimmers green and brown, unlike the modern blue. The atmosphere, although oxygenated, carries a sharp, metallic scent. Lightning storms are frequent. Volcanoes belch ash and gas into skies that shift from pale yellow to orange depending on the hour. The sun, a little dimmer than today, casts a golden light that struggles to pierce the dense clouds above the oceans. Beneath those clouds, Earth's early life is building something astonishing. The continents, though lifeless to the human eye, are coated in microbial mat scarpets of cyanobacteria that blanket shallow lagoons and ancient tide pools. They are slow, but they shape the atmosphere, pushing oxygen into a world still finding balance. We drift lower, through cloud layers heavy with water vapor. Rainfall is intense and persistent in some regions, while others suffer long, stagnant droughts. Winds swirl differently, as if the jet stream itself hasn't yet learned its rhythm. Thunderstorms rise high, striking the surface with more frequency than we are used to. It's not just the weather that feels different, it's the rhythm of the whole planet. As we sweep over the oceans, we see the true empire of life in this time. Early marine ecosystems teem with strange creatures soft-bodied and hard-shelled trilobites scuttle across the ocean floor. Armored, jawless fish drift in slow, pulsing currents. Coral-like structures form early reefs, built not by corals as we know them, but by sponges, and microbial builders. Jellyfish-like beings dance in the shallows, their forms lit from within by sunlight filtered through mineral-rich water. The colors here are surreal: mossy greens, milky blues, rusty reds. The coastlines blur into a spectrum of mineral deposits and ancient algae. From above, they paint brushstrokes along the edge of continents like primitive fingerprints of early life. And then, there are the skies. From the surface, the sky seems closer. Clouds hang lower. The stars are slightly brighter. No cities exist to dim them. The moon hangs larger in the sky, a bit closer than it is today, and the tides it stirs are stronger, pulling the oceans in massive, thunderous waves. Auroras, fed by a magnetic field that pulses stronger than today's, streak across polar skies like serpents of green and violet. We look back once more from the edge of the atmosphere. This Earth, the one from 500 million years ago, still growing, still experimenting. The ecosystems are simple, yet their effects are profound. The oxygen they generate, the carbon they lock away, the sunlight they absorb or reflect, all of it is laying the groundwork for everything that will follow. This is a world caught between chaos and calm. It has survived collisions, fire, and ice, and it will survive much more. But for now, it breathes in the silence of deep time, waiting for its next great transformation. For a long stretch of Earth's history, land was a place of silence. No rustling leaves, no chirping insects, no green to soften the stone. Just wind-swept rocks, scorched under sunlight, carved by storms, and battered by tides. The continents were quiet, empty surfaces wrapped in weather and waiting. The air was different then, thinner near the ground, but heavier with gases no longer common in the modern sky. Carbon dioxide was plentiful, oxygen still rising. Rainfall often arrived as torrential bursts, carving rivulets into raw soil and carrying minerals back into the sea. Lightning struck often, but nothing yet caught fire. There was nothing to burn. The land was dead, and yet, just beneath the surface, hidden in shallow coastal waters and tidal flats, life was preparing a quiet revolution. It began with the simplest of pioneers. Single-celled organisms began to creep onto moist surfaces at the edges of seas. They clung to wet rock and sand, forming slick biofilms-thin sheets of life that shimmered under the sun. These early colonizers were the first to challenge the boundary between ocean and land, and they would not be the last. Over time, they gave rise to more complex communities. Microbial mats grew thicker. Colonies of cyanobacteria and algae formed layered structures that hugged the damp coastlines. They absorbed sunlight and breathed out oxygen. They trapped sediment and slowly built new textures on the land textures that didn't exist before life arrived. The planet's surface was changing, not through force, but through persistence. Eventually, something remarkable happened. A group of photosynthetic organisms developed structures that allowed them to resist drying out completely. They adapted to the harsh winds and intense light of the open land. They didn't grow tall or fast, but they were resilient. They were the ancestors of mosses, liverworts, and hornworts plants, so small and simple that they seemed almost like green skin stretched over the stone. These plants crept inland, inch by inch, following moisture and shelter. They clustered in cracks where rain collected, on slopes that drained slowly, near springs and seeps where water lingered. They formed mats, soft and spongy, which trapped soil particles and slowed erosion. Their presence softened the land, not just in appearance, but in physics. With every patch of moss or lichen that took hold, the landscape began to retain water differently. The ground cooled more slowly, dried out more gradually, and eroded more gently. As these first plants expanded, they altered the atmosphere further. More oxygen was released. Carbon dioxide levels, though still high, began to decline. Clouds formed more easily over green land than over barren rock, and rainfall became more frequent in some regions. The interaction between land and sky deepened. The planet was learning to regulate itself. And these humble pioneers were the teachers. As millions of years passed, plant life became more ambitious. Vascular tissue channels for moving water and nutrients emerged. With it came the ability to grow taller, to reach further inland, to resist the full drying power of the sun. The first upright plants were no more than a few centimeters tall, with no true leaves or roots. But they stood, nonetheless, and in doing so, they caught more light, cast more shadow, and changed the wind patterns near the surface. Spores became the method of reproduction. Lightweight and windborne, they allowed these new plants to spread across continents. Rocky flats became patchy green carpets. Riverbanks turned into narrow ribbons of vegetation. Moist valleys bloomed with life each season, then dried and waited for the cycle to begin again. Still no flowers, no seeds, no trees, but the land was no longer lifeless. It breathed, it grew, it changed. With more plant cover came more weathering. Roots, even primitive ones, reached into cracks and widened them. Rainwater, drawn down into soil held in place by moss and early plants, interacted with rock and unlocked nutrients. New layers formed on the surface-thin soil systems that supported more life. The feedback loop had begun. Plants changed the land, and the land made space for more plants. In time, ferns and horsetails appeared, taller and more complex. Forests, though small and scattered, began to rise. They didn't look like forests today. The colors were different, darker greens, fewer textures. The air was heavier with humidity. The ground was spongy and uneven. Everything was quiet. No birds, no mammals, no insects as we know them. Just wind, water, and the low, steady rhythm of photosynthesis. These early green worlds were fragile, but determined. They were built on persistence, not speed. The plants had no flowers to attract pollinators, no fruit to tempt animals, no bark to protect against grazers, because there were no grazers. Nothing yet had followed life out of the sea in great numbers. Land was a green canvas with no audience, no competition, just endless time to evolve. From above, the change was subtle, but profound. What had once been brown, red, and grey now showed streaks of dark green along river deltas and lake basins. Coastlines began to bloom. Clouds shifted course as moisture cycled differently across vegetated surfaces. Rainfall patterns evolved. Temperatures moderated. The planet itself responded, adapting to this new presence. And still, it continued. Millions of years passed, and each new generation of plants reached a little higher, dug a little deeper, covered a little more. They climbed hills. They bridged gaps. They connected ecosystems, and with them came the groundwork for everything else. The insects, the amphibians, the reptiles, the mammals. But long before any of that, the land belonged to the mosses and the ferns, to the pioneers who asked for nothing but sunlight, water, and time. The transformation of Earth's surface was slow, but complete. From lifeless rock to living skin, from barren lands to green worlds. And in doing so, the planet found a new balanced one that would carry it forward into the next era of life, and toward even greater complexity. Seen from space, Earth has never looked the same for long. Across millions of years, the surface of the planet has been a puzzle in motion, a drifting mosaic of land and water rearranged by invisible forces deep below. Continents are not fixed, they slide, collide, tear apart and merge again. The world of 500 million years ago was not a static canvas, it was alive with movement. Beneath the crust, vast slabs of rock floated on molten layers. This slow churning of Earth's mantle gave rise to plate tectonics, a force that, over time, sculpted the geography of the planet again and again. Mountains rose, oceans opened, and lands once joined were pulled to opposite ends of the globe. This was no random drifting, it was a rhythm. Continents followed patterns, responding to heat, pressure, and the balance of weight between crust and core. Early in this vast timescale, around 500 million years ago, the supercontinent Gondwana dominated the southern hemisphere. It was a colossal landmass, stretching from what is now South America and Africa to Antarctica, Australia, and the Indian subcontinent. To the north, smaller land blocks like Laurentia, Baltica, and Siberia drifted in isolation, separated by shallow seas. These ancient seas shimmered with sunlight, teeming with trilobites, early corals, and the first vertebrates. But above the surface, the view was even more dramatic. From orbit, the Earth was a swirling blue sphere, edged by white clouds and ringed by belts of storms. Near the equator, bands of intense weather pulsed across the ocean, feeding life with rain and shaping coastlines with relentless energy. The poles were not frozen wastes but temperate zones, home to lush greenery and mild climates. No ice caps yet crowned the planet. Instead, forests thrived where glaciers one day would rule. Over time, the lonely fragments of land began to drift closer. Collisions were inevitable. Continents moved at the speed of fingernail growth. But even that glacial pace, stretched over millions of years, carried immense power. When land met land, mountains rose. When land split apart, rifts formed and new oceans emerged. Volcanic activity spiked at these boundaries, reshaping the terrain and injecting vast amounts of carbon dioxide into the atmosphere. As Gondwana shifted northward, it began a slow convergence with the other landmasses. This movement would eventually lead to the birth of Pangaea, the most famous supercontinent in Earth's history. Its formation was a process of violence, and fusion continents slammed together, folding rock into vast mountain ranges, such as the Central Appalachians and the Urals. Massive fault lines carved into the crust, sending tremors across the landscape and reshaping coastlines. The merging of continents altered ocean currents, atmospheric circulation, and even the chemistry of the oceans themselves. From space, the assembling of Pangaea was a slow unification. One by one, the pieces came together until a single gigantic landmass sprawled across much of the globe. It was ringed by the vast Panthalassic Ocean, which covered nearly the entire other half of the planet. The air above this ocean was stable, often still, while the storms and turbulence gathered around the continental margins. Weather patterns danced across its edges, driven by monsoons and vast inland deserts. On land, the appearance of Pangaea was strange by modern standards. Much of the interior was dry and barren. Rain rarely penetrated far beyond the coasts, leaving central regions sunbaked and windswept. Rivers ran long distances from mountains to the sea, cutting through stone and shaping canyons. There were no grasses to bind the soil, no flowering plants to brighten the surface. Instead, conifers, cycads, and giant horsetails dominated the forests, their shadows casting patterns across ferns and mosses below. Despite its arid heart, Pangaea was not lifeless. Coastal zones teemed with ecosystems, and the seas that surrounded it were alive with giant fish, marine reptiles, and corals that built towering reef structures. The diversity of life along the shores created hotspots of activity, both biologically and geologically. Tides sculpted the deltas. Storms reorganized the beaches. Sediment from the land poured into the ocean, feeding the future fossil record. As the planet spun on its tilted axis, the supercontinent's vast shape influenced the seasons. Summers scorched the interior, winters froze it. Without oceans to moderate temperatures, Pangaea experienced extreme swinging between heat and cold, wet and dry. Winds blew dust for thousands of kilometers, reshaping dunes and altering the climate over time. From above, great storms cast shadows over entire regions, marking the pulse of a restless world. Eventually, the very forces that formed Pangaea began to tear it apart. Heat built up beneath the crust, creating rifts and pressure that split the landmass. As it broke apart, new oceans opened, and continents began their slow journey toward their present-day positions. Each stage of this process left a new signature on Earth's face. The Atlantic Ocean emerged. The Indian subcontinent raced northward toward Asia. Australia drifted away from Antarctica. Seen from space, The Earth once again transformed. The outline of the continents changed. The distribution of green and brown shifted. White glaciers began to creep across the poles. Blue currents traced new paths across the ocean. And life, as always, responded. Ecosystems adapted to the moving land, evolving in isolation or merging in bursts of diversity when continents collided again. The continents, even today, are not still. The movement continues, and the shape of the Earth we know now is only temporary. Over millions of years to come, the planet will reorganize itself again. But during the era between 500 to 66 million years ago, it was this restless drifting of continents that shaped the planet's character, setting the stage for the rise of forests, the dance of weather systems, and the astonishing life that followed. The air above prehistoric Earth was not quiet. It was a living, breathing engine powered by the sun, shaped by oceans, and stirred by continents in motion. Weather did not simply pass, it transformed landscapes, nourished ecosystems, and in some cases, triggered extinction. Between 500 and 66 million years ago, the atmosphere was a constant sculptor, wielding wind, rain, and temperature with an intensity that modern Earth rarely witnesses. Early in this stretch of time, the composition of the atmosphere was different. Oxygen levels were lower, then later surged to record highs. Carbon dioxide concentrations fluctuated wildly, sometimes reaching levels 4 to 10 times higher than today. These shifts in greenhouse gases meant that global temperatures often soared, even at the poles. The absence of polar ice for most of this era painted a different climate world, where tropical forests crept into high latitudes and deserts sprawled across supercontinents. When Gondwana drifted beneath the equator, it was subject to monsoon systems driven by the extreme contrast between land and ocean. Vast regions experienced seasonal torrents of rain, followed by long periods of dry heat. Later, when Pangaea formed and sprawled across much of the planet, this monsoonal pattern intensified. The landmass was so massive that its interior became a vast desert, isolated from the moisture-bearing winds of the sea. These deserts were not just empty, they were blasted by sandstorms, scorched by the sun, and visited by only rare, violent rain. Storms in this ancient world were colossal. Towering cumulonimbus clouds could rise higher into the atmosphere than today, fueled by heat and humidity. Lightning cracked across alien skies, sometimes igniting wildfires that swept through dense coniferous forests. Rain did not fall gently. It came in sheets, washing over floodplains, carving through soft earth, and filling ancient river systems that meandered for hundreds of kilometers. In coastal regions and shallow inland seas, tropical storms gained strength. With no modern continents to break their momentum, these systems could grow into massive, long-lasting cyclones. They reshaped coastlines, uprooted vegetation, and drove storm surges deep into land. Sediment layers preserved the marks of these tempest-sharp boundaries between calm deposits and chaotic mixtures of sand, shell, and broken life. Cloud cover, too, was different. The skies over vast oceans were often clear and reflective, while the skies over warm, forested continents brewed thick clouds by midday. The interplay between vegetation and atmosphere was already powerful. Forests pumped water vapor into the air, promoting rainfall. In turn, that rain supported even more plant life, forming a feedback loop that made certain regions lush and others barren when disrupted. During periods of high volcanic activity, the climate turned chaotic. Eruptions released ash and sulfur dioxide into the atmosphere, blocking sunlight and cooling the surface. At the same time, the release of carbon dioxide from the same eruptions added to long-term warming. This push and pull created alternating cycles of heat waves and cooling episodes, some of which triggered mass die-offs or migrations. Oceanic currents, driven by both wind and salinity, also played a central role in global weather. When continents reconfigured, they altered these currents, changing where heat was carried across the planet. Warm currents brought tropical conditions to polar regions. Cold currents created upwelling zones, rich in nutrients but often associated with arid coastal climates. The absence of polar ice caps meant sea levels were consistently higher, flooding large portions of continents and creating shallow, warm seas where weather patterns danced between land and water. Even the tilt and orbit of the Earth's subtle, slow variations known as Milankovitch cycles had profound effects. They shifted the distribution of solar energy, altering the timing and intensity of seasons. These cycles, acting over tens to hundreds of thousands of years, could transform lush landscapes into deserts or freeze warm zones under snow. Though there were no humans to observe these shifts, the fossil record shows how ecosystems responded. Species moved, evolved, or disappeared. As time advanced toward the late Mesozoic, the climate warmed further. Carbon dioxide spiked again, likely from the opening of new oceans and increased volcanic outgassing. Tropical conditions extended from equator to pole. Temperatures at the poles remained warm year-round, allowing forests to thrive where glaciers would one day dominate. Rains were more frequent and widespread, feeding the explosion of flowering plants and the ecosystems that depended on them. Across this entire expanse of time, the weather shaped the story of life on Earth. It influenced where plants could grow, how animals migrated, and even what body shapes were most efficient for survival. Creatures that lived in arid zones developed ways to retain water. Those in stormy coastal regions evolved to burrow, cling, or flee. The atmosphere was not just background, it was a force, as alive and evolving as the biosphere itself. When viewed from space, the patterns were unmistakable. Massive storm systems swirled across open oceans. Rain bands stretched for thousands of kilometers. Deserts bled red into the sky with dust. Green belts of vegetation pulsed with moisture after seasonal rains. The planet glowed with life and motion, each cloud casting a shadow on an ancient Earth forever in flux. By 66 million years ago, as the age of dinosaurs neared its end, the climate was beginning another slow transformation. Subtle changes in ocean circulation and tectonic shifts were setting the stage for cooler climates. The clouds that once towered over jungles would, in time, cast shadows on icy peaks. But in this long prehistoric age, weather had sculpted a world both brutal and beautiful, where the breath of the sky reached into every corner of the living planet. The landscapes of ancient Earth were defined not only by shifting continents or erupting volcanoes, but by the slow, silent rise of plants. Over the course of hundreds of millions of years, life on land transformed from barren, rocky plains into lush green tapestries of towering forests and intricate undergrowth. These prehistoric plant kingdoms were more than scenery. They were engines of change, shaping the atmosphere, stabilizing soils, and creating habitats that would support some of the most iconic creatures in Earth's history. In the early part of this timeline, around 500 million years ago, land was nearly lifeless. The first colonizers were simple moss-like plants and microbial mats, clinging to damp coastal zones. They had no roots, no flowers, and no woody stems, yet they performed a revolutionary task. They began to bind soil, trap moisture, and release oxygen into the air. This modest beginning set the stage for everything to come. By the late Silurian and Devonian periods, vascular plants had emerged. These were the first organisms with internal plumbing tubes that could move water and nutrients through their bodies. With this innovation, plants grew taller and moved farther inland. Club mosses, horsetails, and ferns spread across floodplains and river valleys, creating the planet's first true forests. Their leaves fanned out like primitive solar panels, and their spores drifted on the wind to colonize new terrain. These early forests were strange by modern standards. They had no flowers, no fruit, and no grass. Instead, they were dominated by giant tree ferns, towering lycophytes, and spiny shrubs. Their trunks were often hollow or soft, and they grew in dense, swampy environments. Dead plant matter accumulated into thick mats, and over time, this organic mass would compress into the coal beds we mine today. In these ancient woods, oxygen levels soared, sometimes exceeding 30% of the atmosphere. Wildfires were common, and insects grew to enormous sizes in the hyperoxygenated air. As time moved into the Carboniferous and Permian periods, plant evolution continued. The first seed-bearing plants arrived at gymnosperms like conifers, cycads, and ginkgos. These plants no longer relied on spores and water for reproduction. Instead, they used seeds, allowing them to spread more efficiently across dry landscapes. Vast coniferous forests appeared, covering continents in green spires and thick underbrush. Their resilience helped them thrive in varying climates, from tropical coasts to high mountain slopes. The Mesozoic era brought another turning point. Around 140 million years ago, the first flowering plant angiosperms evolved. They started small, likely appearing as low-growing shrubs or aquatic species. But their advantages were profound. Flowers enabled complex pollination strategies involving insects and wind. Fruits protected seeds and aided their dispersal by animals. Within a short evolutionary window, flowering plants spread rapidly, outcompeting many older plant lineages. By the mid-Cretaceous, flowering plants had taken over much of the world. Forests became more diverse, with broad-leaved trees forming canopies and shrubs filling the gaps below. Grasses began to emerge, though they would not dominate until much later. The spread of angiosperms transformed entire ecosystems. They supported new food webs, provided cover for small animals, and allowed for greater specialization among herbivores and pollinators. From a distance, prehistoric Earth began to resemble something familiar. Forests with layered structures appeared, similar in complexity to those today, but the species were still ancient. Magnolias, laurels, and early palms were among the pioneers. Their leaves were thicker, their flowers simpler, but their ecological role was revolutionary. Some flowering trees reached impressive sizes, spreading their crowns over dinosaur trails and coastal deltas. Beneath these forests, ground cover thrived. Ferns and mosses blanketed the soil. Cycads formed spiky groves. Fungi worked unseen, decomposing fallen trunks and recycling nutrients. The symbiosis between roots and fungi mycorrhiza was already well established, allowing plants to extract minerals from the soil more efficiently. This underground network tied the forest together, responding to environmental stress and even distributing nutrients between species. In wetter regions, mangrove-like ecosystems developed along ancient shorelines. Brackish water nurtured dense plant life, while inland deltas supported swamp forests with thick, woody roots adapted to the shifting sediments. In drier areas, shrubs and conifers adapted to conserve water, developing waxy leaves and deep taproots. The diversity of plant adaptations was staggering, shaped by millions of years of climate oscillations and evolutionary trial and error. Through all of this, plants were not passive. They shaped the weather, drove the carbon cycle, and influenced the evolution of animals. Every tree trunk, every leaf, every creeping vine contributed to the transformation of the planet. They absorbed carbon dioxide and released oxygen. They cooled the ground with their shade and stabilized coastlines with their roots. They softened the edges of harsh landscapes and opened the door for animals to thrive. From space, Earth during these ages would have looked vibrant. Dense forests stretched across continents, green flooded the equator, and extended deep into the poles during warm periods. Patches of brown and gold marked seasonal changes. As flowering plants expanded, so too did the textures and colors visible from above. Forests shimmered in shades of green, broken only by the curves of ancient rivers or the silver gleam of shallow seas. This green revolution, silent, slow, and unstoppable, defined much of what we think of as life on Earth. It provided the foundation for countless ecosystems and paved the way for the flowering world we know today. But in the shadow of these forests, something else stirred the rise of massive creatures whose lives would soon be inseparable from the plants that sustained them. Beneath the surface of prehistoric Earth's oceans lay realms of astonishing complexity and beauty. Stretching from the warm equatorial shallows to the cold abyssal plains, these waters teemed with life, much of it alien by modern standards. Long before the rise of dinosaurs, the seas were the first stage for evolutionary drama. hosting strange creatures, immense reefs, and entire food webs hidden in the blue. During the early Paleozoic, nearly 500 million years ago, the oceans were the heart of life. Trilobites crawled across the seafloor in massive numbers. Brachiopods opened and closed like underwater clams, filtering nutrients from the current. Armored jawless fish drifted near the bottom, their bodies protected by bony plates. In these early seas, sunlight reached into shallow waters, where microbial mats, sponges, and primitive coral-like creatures began forming reef-like structures. The Ordovician and Silurian periods marked a boom in marine biodiversity. Coral reefs took on new forms, built not by the same corals seen today, but by tabulate and rugose corals' ancient ancestors with horn-shaped skeletons and honeycomb textures. These early reefs became underwater cities, housing crinoids with feathered arms and nautiloids with long, conical shells. The warm, calcium-rich oceans allowed these reefs to stretch for kilometers, rivaling the size of modern Great Barrier systems. Throughout the Devonian, often called the Age of Fishes, the oceans deepened in complexity. Armored placoderms, some as long as a bus, prowled the waters with crushing jaws. Sharks appeared in various primitive forms, their bodies more flexible than their earlier armored cousins. Reefs grew even larger, harboring species never seen again after this age. Goniatites, distant relatives of the ammonite, floated in coiled shells through reefs like submarines, while sea scorpion sauropterids lurched through coastal shallows, some exceeding 2 meters in length. The Permian seas saw a slow decline in reef complexity. Cooling waters and tectonic upheaval disturbed marine ecosystems. Still, life thrived in many niches. Brachiopods and bryozoans formed colonies across the ocean floor. Sponges filtered vast amounts of water. In deeper regions, life adapted to darkness, feeding on organic matter drifting down from above. By the end of the Permian, nearly all of it would vanish. The Great Dinger mass extinction of staggering magnitude emptied the seas of over 90% of species, leaving behind silence and sediment. As Earth recovered in the Triassic and into the Jurassic, marine life returned with new forms. Corals evolved again, this time giving rise to modern scleractinian species that would dominate reef building. Ammonites exploded in diversity, developing elaborate shell patterns and tightly coiled forms. Ichthyosaurs reptiles that resembled dolphins glided through open waters, hunting squid and fish. Marine crocodiles cruised coastlines, while filter-feeding plesiosaurs hunted in pods beneath sunlit waves. Jurassic reefs rebuilt themselves in warm, shallow inland seas. They weren't continuous like coral belts today, but formed scattered patches where conditions allowed. Beneath their arches, crabs, starfish, and early lobsters flourished. Marine plants like algae and kelp began colonizing shallower depths, anchoring to rocks and providing food for herbivores. The water was often clearer than today, with fewer microscopic plankton clouding the surface, allowing sunlight to pierce deeper. As the Cretaceous unfolded, marine ecosystems grew even more dynamic. The oceans flooded low-lying continents, creating vast inland seas. In North America, the western interior seaway stretched from the Arctic to the Gulf of Mexico, teeming with life. Mosasaurs, the apex predators of their time, dominated these waters. With long jaws and powerful tails, they hunted turtles, ammonites, and even each other along the seafloor. Burrowing clams and echinoderms formed the base of complex food webs. Planktonic life flourished. Coccolithophores and foraminifera bloomed in massive numbers, contributing to the chalk deposits that would later become the cliffs of Dover. These tiny organisms, despite their size, played an outsized role in the carbon cycle, absorbing carbon dioxide and releasing oxygen. When they died, their skeletons drifted down to form thick marine sediments, painting the seafloor in white dust. Life in the deep oceans was less visible, but no less remarkable. Thermal vents spewed mineral-rich water, forming chimney-like structures. Entire ecosystems clustered around these vents, sustained not by sunlight but by chemosynthesis. tube worms, blind shrimp, and sulfur-eating bacteria thrived in total darkness, a parallel world isolated from surface events. Currents shaped life on every scale. They distributed heat, nutrients, and larvae. During warmer periods, ocean circulation was sluggish, leading to stagnant zones and anoxic events episodes where oxygen vanished from vast stretches of water, causing localized extinctions. At other times, strong currents stimulated plankton growth and brought cold, nutrient-rich water to the surface, triggering blooms that sustained fish populations and reef expansion. From above, ancient oceans shimmered in tones of sapphire and emerald. Shallow continental shelves glowed turquoise, where sunlight lit coral reefs and kelp forests. Deeper trenches appeared as indigo voids, hiding leviathans and darkness. At night, bioluminescent life flickered in the shallow's jellyfish, dinoflagellates, and glowing worms painting the water with shifting light. These oceans were alive, not only with motion but with memory recording each shift in temperature, each pulse of evolution, and each collapse and renewal. Throughout this 434 million year span, the oceans were more than background. They were crucibles of change, laboratories of evolution, and reservoirs of resilience. They preserved life during mass extinctions and seeded it anew when land was empty. They were, and remain, the planet's most enduring realm. From the vast silence of space, Earth has always appeared as a shifting canvas, its colors and contours constantly in motion. Between 566 million years ago, the planet transformed in ways both subtle and cataclysmic. Seen from orbit, these changes were etched in the slow drift of continents, the rise of mountain chains, the retreat of ancient seas, and the waxing and waning of ice across the poles. In the early Paleozoic, around 500 million years ago, Earth's continents were fragmented into scattered landmasses. Gondwana stretched across the southern hemisphere, a massive supercontinent comprising what would one day become South America, Africa, India, Antarctica, and Australia. North of it floated smaller blocks Laurentia, Baltica, and Siberia surrounded by vast, shallow oceans. From space, much of the planet was ocean blue, dotted with green and brown islands, fringed by white reefs in the warm equatorial belt. As the Ordovician and Silurian periods unfolded, sea levels rose dramatically. Shallow seas spilled across continental interiors, transforming lowlands into inland seas. From orbit, the continents appeared drowned, their shapes softened by water. Narrow coastlines expanded into flooded plains, with coral reefs and marine platforms glowing beneath the sunlit surface. During the Devonian, the outlines of continents began to shift. Land masses moved steadily northward. In the southern hemisphere, Gondwana tilted and rotated. From space, deserts bloomed in its interior, while mountain ranges began pushing skyward where plates collided. Forests spread across some regions. Dark green swaths of early vascular plants like ferns and club mosses marked the land. Rivers meandered across the continents like silver threads, feeding into shallow marine basins. By the Carboniferous period, Earth's face had become even greener. Vast coal-forming swamps sprawled across tropical latitudes, especially in what is now Europe, Asia, and North America. From space, these regions appeared deep green and humid, broken by vast deltas and swampy lowlands. The equator cut across continents blanketed in thick vegetation, while polar regions began to show hints of glaciation white caps spreading across the southern pole of Gondwana. As the Permian began, around 299 million years ago, Earth entered an era of consolidation. The scattered continents merged into one vast landmass Pangaea. From above, it dominated the globe, an enormous brown and green supercontinent ringed by ocean. The vast interior of Pangaea was arid and dusty, with shifting deserts and dry basins. Mountain ranges, such as the Ural chain, scarred the continent like wrinkled seams. Surrounding it, the single vast ocean panthalassa churned in shades of blue and grey, with immense storm systems forming over its unbroken waters. This supercontinent state would not last. As Pangaea began to rift during the Triassic, dark cracks appeared from space, marking the birth of new oceans. Volcanic activity surged along fault lines. Magma rose from the mantle, creating linear scars that eventually widened into new seaways. Lush green patches returned to coastal areas, especially near the Tethys Ocean, which began carving its way between future Africa and Eurasia. By the Jurassic period, Pangaea had split into two major landmasses, Laurasia in the north and Gondwana in the south. The planet's face changed dramatically. From orbit, rifting valleys and shallow seas glimmered along the equator. Dark green forests draped much of Laurasia, while Gondwana's southern reaches began to cool, developing icy highlands and alpine snowfields. The Tethys Ocean expanded, its turquoise waters dotted with reef systems and island chains. As the Cretaceous era advanced, tectonic drift accelerated. From the vacuum of space, the continents could be seen breaking apart further south. America drifted westward, pulling away from Africa. India began its solitary journey northward. Shallow epicontinental seas like the western interior seaway in North America split continents in two. These inland oceans gleamed under sunlight, stretching over thousands of kilometers, home to vast marine ecosystems. Green covered much of the visible land. Angiosperms flowering plants spread rapidly across the planet, creating new shades of green in the forests and plains. River deltas shimmered like veins. Mountain chains rose in fits and starts, particularly in the west of what would become North America, where tectonic compression built the first outlines of the Rocky Mountains. Climate patterns, too, were visible from orbit. During warm periods, clouds gathered densely over the equator, forming monsoon systems and tropical storms. Near the poles, Earth remained largely ice-free for most of this time. The southernmost tip of Antarctica, although positioned over the pole, was covered not in ice but in conifer forests and wetlands. From space, it appeared as a green cape under a pale sky. At night, the Earth's surface held no artificial light, only the faint glow of bioluminescent plankton in coastal waters. Meteor strikes, though rare, left scars that could be seen from orbit-circular basins filled with water or uplifted rock, silently marking catastrophic moments in Earth's past. Clouds moved in vast spirals, tracing the paths of ancient jet streams. Dust storms blew from inland deserts into the sea. Polar storms formed enormous cyclones, swirling over the Southern Ocean. From space, the dynamic atmosphere revealed patterns of circulation and heat, driven by the sun and the spin of the planet. As the Cretaceous drew to a close, Earth was preparing for another dramatic shift. From orbit, a bright blue world of fragmented continents, inland seas, and living oceans slowly turned, unaware that a massive asteroid had begun its approach. Soon, the view from space would show more than tectonic motion, and cloud cover it would show a world in shock, a surface momentarily lit by fire, dust, and darkness. In the beginning, the land was barren. The wind swept across empty rock, and only the lichen and microbial mats clung to surfaces near coastlines. But over millions of years, life advanced. From simple mosses to towering forests, plants would transform the surface of the earth, painting it green and changing the very air that animals would breathe. During the early Paleozoic, around 500 million years ago, the land remained lifeless while the oceans teemed with activity. It wasn't until the Ordovician period that the first true plantstony, non-vascular species resembling modern liverworts began to colonize moist coastal rocks. They had no roots, no stems, and no leaves. But they laid the foundation. From above, they would have appeared as thin green films stretching across the damp lowlands. As the Silurian and Devonian periods arrived, evolution pushed forward. Plants developed vascular tissue, allowing them to grow taller and draw water from the ground. Roots dug into the soil, anchoring plants in place. Leaves emerged, spreading to catch sunlight. This was the age of the first true forests. Giant horsetails and club mosses formed dense green stands across the continents. Some grew up to 30 meters tall, despite being relatives of the tiny mosses that came before. These primitive forests shaped the climate, pulling vast amounts of carbon dioxide from the air and releasing oxygen in return. From a distance, Earth's surface now wore a green veil. Vast wetland forests, especially near the equator, covered lowland regions. Spore-based plants dominated. Their reproductive cycles were still tied to water, so they thrived in humid environment swamps, floodplains, and coastlines. As these plants died and piled into the wetlands, their remains would compress over millions of years into thick coal bedsown of the planet's most enduring legacies from this era. Then came the rise of the seed. By the late Devonian and Carboniferous periods, plants had evolved seed-san innovation that allowed them to spread across drier regions. Seed ferns and early conifers began pushing into upland zones and arid climates. Their growth freed plants from the constant need for water to reproduce. Forests expanded. The atmosphere grew rich in oxygen, reaching levels much higher than today. Insects grew larger in response. With every passing million years, plants reshaped the biosphere, fueling new evolutionary pathways. The Permian brought change. Climates grew drier. Many swamp-loving species vanished. Gymnosperm seed-bearing plants like conifers, cycads, and ginkgos rose in their place. They spread across the supercontinent Pangaea, enduring extreme conditions. Their waxy needles and protective cones made them resilient. From the sky, Pangaea's once lush equator now displayed more muted shades of green and brown. Forests gave way to shrublands and high-altitude woodlands. Deserts expanded in the continent's interior. But this age of ancient plants would not last unchallenged. After the mass extinction at the end of the Permian, the Triassic saw the rebirth of forests. Ferns reappeared first, carpeting landscapes in green. Cycads and conifers followed, forming the backbone of terrestrial ecosystems. Yet, something new stirred beneath the canopy. Small and unassuming, flowering plant angiosperms were just beginning to emerge. It was during the Cretaceous that they exploded across the planet. Insects and flowers co-evolved in a delicate dance. Petals, scents, and colors drew pollinators, fruit-encased seeds, and lured animals. From tropical rainforests to alpine slopes, flowering plants diversified into countless forms. Grasses began to spread across open plains, replacing ferns and cycads in many ecosystems. Within just a few million years, angiosperms went from background species to planetary rulers. From orbit, Earth changed again. Instead of endless conifer forests, now there were complex mosaics broadleaf forests, grasslands, savannas. Flowering trees bloomed seasonally in dazzling colors. Green still dominated, but now it came in 1,000 subtle shades. These new forests nurtured new life. Herbivorous dinosaurs adapted to feed on tough leaves, sweet fruits, and fibrous stalks. Some migrated with the flowering seasons. Others evolved specialized jaws and stomachs to digest the new plant types. In turn, the forest spread further, stabilized by the animals that consumed and dispersed their seeds. Beneath the surface, the roots of flowering trees held the soil together. They shaped rivers and carved valleys. They influenced rainfall patterns, cooling the land beneath their canopies. They even altered the chemistry of the oceans by controlling the runoff of minerals and nutrients. By the end of the Cretaceous, plants had redefined the Earth. They covered mountains, filled valleys, and colonized islands. Mosses still lingered in moist shadows. Ferns thrived in dappled undergrowth. Conifers towered in colder regions, but it was the flowering plants that had taken over the world. Then, in an instant, the bloom was interrupted. The asteroid impact at the close of the Cretaceous would darken the skies and silence the forests. For months, sunlight barely reached the surface. Photosynthesis stalled. Leaves withered. Pollen ceased to drift through the air. Yet in the shadows and the soil, seeds waited, and when the skies cleared, the green returned. Always, the plants came back. Earth's climate system has always been in flux, driven by forces both subtle and immense. Over the past 500 million years, the planet has endured dramatic shifts in temperature, atmospheric composition, and weather patterns. From the hot, humid greenhouse world of the early Paleozoic to the icehouse conditions of the late Paleozoic and beyond, the Earth's climate was never static. From space, Earth's shifting weather patterns, continents, and oceans were constantly changing. In the Cambrian period, around 500 million years ago, the planet was in the midst of a warm period. The atmosphere had a higher concentration of carbon dioxide and other greenhouse gases than today. This created a global greenhouse effect, trapping heat in the atmosphere and creating a climate that was hot and humid. Polar regions were free of ice, and the planet had no permanent ice caps. Seas flooded the land, creating a shallow, warm environment that supported the emergence of the first complex marine ecosystems. From orbit, the planet would have appeared mostly blue, its oceans glowing with the reflection of a pale sun. The land, still in the grip of early life forms, was barely visible tiny patches of green from simple mosses clinging to the coastal rocks. As time passed and the Ordovician period began, Earth's climate fluctuated between warm and cool periods, influenced by the movement of continents and the changing position of the sun. Sea levels rose and fell in response to changing global temperatures. The early Ordovician was marked by warmth, but by the end of the period, a dramatic cooling took place, leading to a global ice age. This glaciation, called the Andean-Saharan Ice Age, covered much of the southern hemisphere, including what is now Africa, South America, and Australia. Earth from space would have appeared dramatically differenter, colder, more desolate landscape, with vast ice sheets stretching across much of the southern continents. Oceans retreated, leaving behind expansive, barren shorelines. During the Silurian period, temperatures gradually began to warm again. The climate stabilized, allowing for the diversification of plant life. Forests began to spread across the land, and the first vascular plants began to take hold. The carbon dioxide levels in the atmosphere remained relatively high, keeping temperatures warm. This created a humid, tropical environment, especially along the equator. From space, the planet would have looked lush and green, with thick forests blanketing the land. Shallow seas continued to cover large portions of the continents, feeding marine ecosystems and influencing the climate of adjacent landmasses. The Devonian period saw the rise of the first forests and the spread of plants across the land. During this time, the carbon dioxide levels remained high, contributing to the continued warmth of the planet. However, by the end of the Devonian, another cooling period began to take hold. This cooling was partially driven by the evolution of plants, which began to draw down carbon dioxide from the atmosphere through photosynthesis. This process gradually lowered the greenhouse gases in the air, causing global temperatures to drop. From space, the cooling would have been apparent as the polar regions began to freeze. Vast, icy expanses began to form at both poles, leading to the formation of ice sheets that would persist throughout the Paleozoic era. As the Carboniferous period began, the planet entered one of its warmest phases. Carbon dioxide levels were once again high, and the climate was tropical. Lush rainforests and swamps dominated the landscape, especially in the regions that would eventually become coal deposits. The Carboniferous period was marked by the rapid evolution of plants, especially ferns and giant trees. These plants absorbed enormous amounts of carbon dioxide, which contributed to a drop in atmospheric carbon levels over time. This, combined with the cooling effects of the plants, led to the gradual onset of glaciation. By the end of the Carboniferous, much of Earth's surface had cooled, and ice sheets began to form in the southern polar regions. From space, the planet would have appeared green and humid in the equatorial regions, with ice beginning to creep across the poles. As the Permian period began, the climate grew more arid. Much of the planet was dominated by deserts and dry, open landscapes. This was partially the result of the supercontinent Pangaea, which had formed by this time. The vast landmass altered atmospheric circulation patterns, leading to extreme fluctuations in temperature. The interior of Pangaea became dry and hot, while coastal areas saw more temperate conditions. From orbit, Earth would have appeared brown and dusty in the interior, with vast dry plains and deserts. Ice sheets were largely confined to the southern polar region, and the planet as a whole had a more arid, desert-like appearance. The warm, humid climates that had once dominated much of the Earth's surface had given way to harsh, dry conditions. The Triassic period marked the beginning of a new climate phase. As Pangaea began to rift and break apart, the climate began to stabilize. Temperatures were generally warm, and the planet was largely ice-free. However, this stability was not without its fluctuations. Regional climates varied, with warm tropical conditions in some areas and drier, desert-like environments in others. The early Triassic was marked by a hot, dry climate, which began to shift toward a more humid environment as plant life diversified and ecosystems recovered from the Permian mass extinction. From space, the planet would have appeared more diverse, with green regions flourishing along the equator and deserts pushing outward from the continents. By the Jurassic period, Earth's climate was largely warm and humid. This was a time of great plant and animal diversification. The breakup of Pangaea created vast coastlines, leading to an increase in the amount of shallow seas, which helped stabilize the global climate. The atmosphere was rich in carbon dioxide, and temperatures remained high, fueling the rapid growth of plants and the rise of the first true forests. From orbit, the planet would have looked vibrant, lush, green forests spreading across the land, with shallow seas creating sparkling blue regions along the coasts. The Cretaceous period brought further changes to the planet's climate. As the continents continued to drift, ocean currents shifted, and global temperatures fluctuated. Earth's atmosphere remained warm, with a greenhouse climate regime in full swing. The planet was lush with vegetation, and plants thrived in the warm, humid conditions. The polar regions were free of ice, and global sea levels were high. From space, the Earth would have appeared warm and inviting, with expansive forests covering much of the land. Vast inland seas stretched across continents, dividing landmasses and creating rich, diverse ecosystems. However, as the Cretaceous drew to a close, Earth's climate began to change once again. The asteroid impact at the end of the period triggered a rapid cooling event. Dust and debris filled the atmosphere, blocking sunlight and causing temperatures to plummet. From orbit, Earth would have appeared dark, its surface covered by a thick cloud of smoke and ash. This cooling event marked the beginning of a new climate phase, the transition into the cooler, icehouse conditions of the Tertiary period. Throughout the Cenozoic era, Earth's climate would continue to fluctuate between warm and cold periods. The planet's weather patterns would become more complex as new climates and ecosystems developed. From space, Earth would appear as it does today, an ever-changing, dynamic world with shifting weather patterns, storm systems, and changing landscapes. Yet, the planet's climate, despite its variations, would continue to be shaped by the forces of plate tectonics, atmospheric composition, and the cycling of carbon and water. In the end, the Earth's climate history tells the story of a planet constantly in motion, with each shift in temperature and weather patterns shaping the ecosystems and life that thrive upon it. The oceans of ancient Earth were vastly different from those we know today. During the past 500 million years, the seas have gone through dramatic transformations, both in terms of geography and the life they supported. From the warm, shallow seas that dominated much of the planet in the Cambrian to the deep, nutrient-rich waters that shaped the ecosystems of the Cretaceous, the ancient oceans were a dynamic environment in which life evolved and thrived in ways we can only begin to understand. In the Cambrian period, life in the oceans was just beginning to diversify. The seas were shallow and teeming, with a variety of simple life forms. Soft-bodied creatures dominated, their fragile exoskeletons offering little protection from the predation of early marine life. Oceans were warm and relatively calm, with little separation between shallow coastal waters and deeper oceanic regions. From space, the planet would have appeared predominantly blue, its shallow seas reflecting the sun's rays in a dazzling display. Life was beginning to flourish in the oceans, with early forms of plankton, arthropods, and the first vertebrates making their appearance. As time moved into the Ordovician period, the oceans deepened, and life in them became more complex. Coral reefs began to form, providing shelter for a wide variety of marine creatures. The first large, predatory fish emerged, hunting smaller marine life in the increasingly crowded seas. The oceans were becoming more stratified, with warm, oxygen-rich waters near the surface and colder, deeper regions below. These changes in the ocean structure and temperature began to foster the evolution of more specialized forms of life. From space, the oceans of the Ordovician would have appeared as an ever-expanding patchwork of shallow seas and deeper waters, the surface reflecting the warm climate that dominated much of the period. During the Silurian and Devonian periods, the oceans saw an explosion of diversity, especially in the development of fish. The seas were home to an astounding variety of marine life, from small, filter-feeding creatures to large, predatory fish. The rise of jawed fish during this time marked a significant milestone in the history of life. These fish were more efficient hunters, and their emergence triggered a cascade of evolutionary changes in the oceanic food chain. The Silurian oceans were dominated by coral reefs, which provided an ideal environment for the growth of marine life. From space, the planet would have appeared vibrant, its oceans teeming with life, while the coastal areas were dotted with flourishing reefs. The atmosphere, still rich in carbon dioxide, contributed to a warm, humid climate that fueled the growth of these marine ecosystems. The Devonian period, often referred to as the Age of Fish, witnessed the proliferation of fish species in both the oceans and the rivers. The seas were filled with giant placoderm fish, cartilaginous sharks, and the first ray-finned fish. Deep-sea ecosystems were also beginning to take shape, with organisms adapting to life in the darker, colder depths. The oceans were a dynamic, ever-changing environment, with new species emerging to fill every available niche. From space, Earth would have appeared like a water world, with an abundance of blue reflecting the thriving marine ecosystems. Land-based life was still in its infancy, but the oceans remained the dominant force in shaping the planet's biodiversity. Moving into the Carboniferous period, the oceans were dominated by diverse marine life forms. The increase in plant life on land contributed to the formation of vast swamps and wetlands, which in turn supported even more complex ecosystems. The seas saw the rise of ammonoids, crinoids, and giant marine arthropods. The Carboniferous oceans were warm and teeming with life, with both the shallow coastal waters and the deep oceans providing habitats for an incredible array of organisms. The rise of these organisms was driven by the high levels of oxygen in the atmosphere and the abundance of nutrients in the oceans, which allowed life to thrive. From space, Earth would have appeared green in the equatorial regions, with vast swamps dotting the continents and a bright blue ocean alive with movement beneath the surface. By the Permian period, the oceans had undergone significant changes. The supercontinent Pangaea, which began to form during this time, altered the geography of the planet. Shallow seas that once covered much of the Earth's surface began to shrink, while deep ocean basins became more defined. The seas of the Permian were home to a wide variety of marine life, including the first true marine reptiles. Early ichthyosaurs and plesiosaurs began to dominate the seas, while giant sharks and predatory fish patrolled the oceans. The climate was hot and dry, especially in the interior regions of Pangaea, but the oceans remained warm and teeming with life. From space, the Earth would have appeared mostly arid, with the oceans serving as the last bastion of life in a largely desolate world. The waters would have looked still and calm, with few visible signs of the powerful changes taking place beneath the surface. As the Triassic period began, the oceans experienced another phase of diversification. The breakup of Pangaea led to the formation of new oceans and seas, creating new habitats for marine life to evolve and thrive. Marine reptiles, such as ichthyosaurs and plesiosaurs, became dominant in the seas. The oceans were filled with fish, both large and small, and the first true marine ecosystems began to take shape. The temperature of the oceans was warm, and shallow seas covered much of the planet's surface. From space, the planet would have appeared vibrant, with vast expanses of shallow, warm waters surrounding the newly formed continents. The oceans were alive with the movements of ancient creatures, their presence creating an ever-changing rhythm beneath the surface. The Jurassic period saw the oceans become even more populated with marine reptiles, including the rise of the giant long-necked plesiosaurs and the massive ichthyosaurs. The oceans were teeming with life, from small plankton to enormous marine reptiles. Coral reefs flourished in the warm, shallow seas, providing homes for a wide variety of organisms. The oceans were full of nutrients, which supported the growth of marine life in every corner of the planet. From space, the planet would have appeared blue and vibrant, with coral reefs dotting the warm seas and vast areas of shallow water, supporting an incredible diversity of life. The Cretaceous period brought further diversification in the oceans. The separation of the continents continued, and ocean currents shifted, altering the distribution of nutrients and creating new marine ecosystems. The oceans of the Cretaceous were home to a wide variety of marine life, including giant mosasaurs, giant sharks, and the first true whales. The seas were warm and teeming with life, with coral reefs continuing to thrive and the oceans becoming more stratified. From space, the planet would have appeared dynamic, its oceans filled with movement and life. Warm seas would have been visible, dotted with islands and vast coastlines teeming with marine creatures. However, as the Cretaceous drew to a close, a catastrophic event changed the course of life in the oceans. The asteroid impact at the end of the period triggered a mass extinction that wiped out the majority of marine species, including the marine reptiles that had once dominated the oceans. The oceans from space would have looked dark, their surfaces obscured by the dust and debris ejected into the atmosphere. The once thriving marine ecosystems were suddenly quiet, their future uncertain as the planet entered a new phase of recovery. Throughout the Cenozoic era, the oceans continued to evolve, as new forms of life took hold, including whales, dolphins, and other marine mammals. The oceans gradually began to recover from the mass extinctions. From space, the Earth would have appeared as it does today, its oceans still teeming with life, a testament to the resilience of life on Earth. The evolution of terrestrial ecosystems marks one of the most significant chapters in the history of life on Earth. While the oceans had been the cradle of life for millions of years, the land remained an inhospitable environment until the Silurian period. This transformation would unfold slowly, with plant life initially leading the charge, followed by the gradual colonization of the land by animals. Over time, terrestrial ecosystems would evolve into complex webs of life that rivaled the oceans in their biodiversity and intricacy. The Silurian period saw the first signs of life on land. While the oceans were teeming with diverse organisms, the land was barren, except for microbial life and some primitive plants. The first plants to colonize the land were simple mosses and liverworts, which could survive in the harsh conditions of the dry, exposed surface. These plants played a crucial role in shaping the terrestrial environment, as they began to convert carbon dioxide into oxygen, slowly altering the composition of the atmosphere. The appearance of these early plants would have been relatively subtle, with small green patches dotting the barren landscape. From space, Earth would have appeared mostly barren, with only small pockets of green emerging along the edges of the oceans and rivers. By the Devonian period, terrestrial ecosystems had begun to take shape more dramatically. The first true forests began to grow, with ferns, lycophytes, and early seed plants dominating the landscape. These plants were the foundation for the development of more complex ecosystems, creating the first true terrestrial habitats. These ancient forests would have been lush and green, providing shelter and food for a variety of organisms. From space, the planet would have appeared more varied, with patches of green spreading across the landmasses as plants began to take hold in the interior regions. The rise of plants on land also paved the way for the next phase in the evolution of terrestrial ecosystems, the colonization of the land by animals. During the late Devonian, the first animals began to venture onto land. These early land-dwelling creatures were simple, arthropod-like animals, such as millipedes and scorpions, which were capable of surviving in moist environments. The rise of these early land animals was closely tied to the evolution of plants, as they provided new niches for these animals to occupy. These creatures would have been small and low to the ground, scurrying across the damp, moss-covered surfaces of the ancient forests. The land, though still a challenging place for life, was slowly becoming more hospitable. In the Carboniferous period, the evolution of both plants and animals reached new heights. The forests grew even more complex, with towering trees and vast swampy wetlands stretching across much of the planet. The rich, oxygen-rich atmosphere allowed plants to grow to enormous sizes, creating dense, lush environments that were home to an ever-increasing diversity of life. Giant insects, such as dragonflies with wingspans of over 2 feet, dominated the skies, while amphibians began to venture further onto land. These amphibians, descendants of fish, were among the first vertebrates to make the transition from water to land. They would have been relatively small, with smooth, moist skin that required them to stay near water sources. From space, Earth would have appeared incredibly vibrant, with thick, green forests and marshes covering much of the land, while the atmosphere, dense with oxygen, would have appeared hazy and heavy. The transition from amphibians to reptiles marked another significant milestone in the evolution of terrestrial ecosystems. During the late Carboniferous and into the Permian period, reptiles became the dominant land animals. These creatures were more adapted to the dry, land-based environment than amphibians, thanks to their ability to lay eggs that could survive out of water. Reptiles, including early ancestors of dinosaurs, began to spread across the planet, filling every available ecological niche. Their success was facilitated by the development of more complex and varied plant life, which provided them with abundant food sources. The terrestrial ecosystems during this time were diverse, ranging from dense tropical forests to arid deserts. From space, Earth would have appeared increasingly variegated, with green forests and arid landscapes interspersed across the planet's surface. The planet was becoming a dynamic and diverse world, with life flourishing in almost every environment. The Permian period also marked a time of significant geological change, with the formation of the supercontinent Pangaea. This vast landmass altered the planet's climate, leading to more extreme fluctuations between hot and cold regions. The ecosystems of the Permian were shaped by this shifting climate, with deserts, forests, and swamps all coexisting in different regions of the planet. The rise of dinosaurs, the dominant terrestrial vertebrates, occurred during this time, although they would not fully flourish until the Triassic. From space, the planet would have appeared more unified, with large landmasses covering much of the surface, surrounded by vast oceans. The ecosystems on land, though still evolving, were beginning to resemble the more familiar ones we recognize today. The Triassic period marked the beginning of the age of dinosaurs, a time when terrestrial ecosystems became increasingly complex. The rise of dinosaurs was closely tied to the spread of gymnospermstone-bearing plants that dominated much of the planet's forests during this period. These plants provided a new food source for herbivorous dinosaurs, which in turn supported a growing population of carnivorous species. The ecosystems of the Triassic were diverse, with vast forests of conifers stretching across much of the land, and deserts, swamps, and lakes providing habitats for a variety of creatures. From space, Earth would have appeared more complex, with large landmasses dominated by forests and smaller patches of arid land, while the atmosphere remained dense and humid. During the Jurassic period, the terrestrial ecosystems reached new heights of complexity. The dominance of dinosaurs continued, with both herbivorous and carnivorous species growing to massive sizes. The oceans also supported large marine reptiles, while on land, the first true birds began to evolve from small theropod dinosaurs. The plant life during this time became even more diverse, with ferns, cycads, and conifers forming dense forests. The planet from space would have appeared highly diverse, with vast stretches of lush, green forests, some of which stretched across the continents, while large, fertile plains supported herds of herbivorous dinosaurs. The atmosphere, rich in carbon dioxide, would have contributed to the warm, tropical climate, supporting the flourishing of life. The Cretaceous period saw further diversification of terrestrial ecosystems, with flowering plants beginning to spread across the globe. These plants provided new food sources for herbivorous dinosaurs, which in turn supported the rise of even more specialized predators. The climate continued to warm, and the planet's ecosystems became even more dynamic. From space, the Earth would have appeared more vibrant, with rich, green vegetation covering the land masses, while the oceans teemed with life. The end of the Cretaceous, however, would bring an end to this golden age of dinosaurs. The asteroid impact at the end of the period led to the mass extinction of the dinosaurs, wiping out many terrestrial ecosystems in the process. From space, Earth would have appeared dark and still, its surface blanketed by dust and debris, marking the end of an era. As the Cenozoic era began, the terrestrial ecosystems began to recover. Mammals, which had been relatively small during the age of dinosaurs, began to diversify and dominate the land. Forests, grasslands, and deserts once again became the habitats for these new forms of life. The planet would have appeared much like it does today, with large areas of green forests, grasslands, and arid deserts dotting the continents. The rise of mammals, birds, and flowering plants led to the development of the modern terrestrial ecosystems we recognize today. After the mass extinction event that wiped out the dinosaurs at the end of the Cretaceous period, the world experienced a profound transformation. The end of this era opened the door for mammals to rise and take on more prominent roles within terrestrial ecosystems. While mammals had always existed alongside dinosaurs, they were relatively small and inconspicuous, living in the shadows of the great reptiles. However, with the extinction of the dinosaurs, mammals quickly adapted to fill the vacant ecological niches left by their prehistoric predecessors. The early Cenozoic era, known as the Paleogene period, marked the beginning of the age of mammals. As the Earth began to recover from the impact event, new ecosystems began to emerge. Without the dominance of dinosaurs, mammals began to evolve into a wide variety of forms, from tiny insectivores to massive herbivores and carnivores. The extinction of the dinosaurs allowed for a dramatic increase in the diversity of mammalian life, as the environmental conditions became more favorable for these creatures. Forests, grasslands, and wetlands flourished, providing abundant resources for mammals to thrive. One of the most notable evolutionary developments during this time was the rise of placental mammals. These mammals, which included the ancestors of modern-day primates, carnivores, and herbivores, gave birth to live young, a significant advantage over earlier mammals that laid eggs. This adaptation allowed placental mammals to colonize a variety of habitats, from dense forests to open grasslands. Their ability to give birth to fully developed young meant that they could more effectively exploit available resources, leading to their rapid diversification. The landscape itself underwent significant changes as well. The Earth's climate continued to stabilize, with forests once again dominating much of the land. Tropical rainforests spread across the equator, while temperate forests began to develop in the cooler regions. Vast grasslands began to appear, especially in the areas where the climate was becoming drier. These new ecosystems provided the perfect environment for the evolution of large herbivorous mammals, such as the ancestors of modern-day elephants, horses, and rhinoceroses. Alongside these herbivores, the first large carnivorous mammals, such as early members of the carnivorous order of mammals, began to evolve. From space, Earth would have appeared as a dynamic world, with large, varied landscapes taking shape. Patches of lush green forests covered much of the land, while vast open plains began to emerge in areas where the climate was becoming more arid. As the Earth cooled and the ice caps began to form, polar regions would have been dominated by tundra and glaciers, while the tropics remained warm and humid. The planet was no longer dominated by the reptilian giants of the past, but was now becoming a world ruled by mammals. The development of large herbivores during this period set the stage for the rise of large predators. With abundant plant life providing sustenance, herbivorous mammals grew in size and number, which, in turn, supported the evolution of larger carnivores. These predators, some of which were among the first true carnivores, had to adapt to a changing world. As mammals became more diverse, their interactions with one another also evolved. Herbivores and carnivores began to develop complex relationships, with predators hunting in packs or evolving specialized hunting strategies to capture prey. One of the most significant adaptations of mammals during the early Cenozoic was the development of different feeding strategies. Herbivores evolved specialized teeth and digestive systems to process plant material more efficiently, while carnivores developed sharp teeth and claws to capture and consume prey. Omnivores, meanwhile, evolved a more varied diet, allowing them to exploit a wide range of food sources. These evolutionary developments helped mammals thrive in the changing ecosystems of the Paleogene period. During the Eocene epoch, the diversity of mammals continued to grow. Forests expanded, and the first true primates appeared, marking the beginning of the evolutionary lineage that would eventually lead to humans. At the same time, the first large marine mammals, such as early whales, began to evolve. These creatures ventured back into the oceans from which their land-dwelling ancestors had emerged millions of years before. Their return to the seas marked the beginning of a new chapter in the history of mammals. The early Cenozoic era was also a time of significant geological activity, with the movement of tectonic plates continuing to reshape the planet. The continents slowly drifted to their current positions, creating new geographical features and altering climate patterns. The closure of the Tethys Sea, for example, led to the formation of mountain ranges, such as the Himalayas, and influenced the climate of the surrounding regions. These geological changes would have a profound impact on the development of terrestrial ecosystems, as new environments were created and old ones were altered. As the Earth continued to cool, the development of new ecosystems played a crucial role in shaping the course of mammalian evolution. Grasslands, which were initially sparse, expanded as the climate continued to dry out, providing ample food sources for herbivorous mammals. The diversification of grassland ecosystems led to the evolution of new herbivorous mammals that were adapted to grazing on these open plains. These mammals, such as early ancestors of modern-day horses and bison, played a crucial role in shaping the landscapes they inhabited, as their grazing habits contributed to the expansion of grasslands and the reduction of forests in certain regions. By the Miocene epoch, the Earth's ecosystems had become even more complex. The climate continued to cool, leading to the development of more distinct seasons in many parts of the world. Forests continued to thrive in some regions, while grasslands spread across the planet's interior. The rise of savannas, where grasslands mixed with scattered trees, provided ideal habitats for both herbivores and carnivores. The evolution of large grazing mammals, such as antelopes and early members of the bovine family, was a key feature of this period, as these animals adapted to the open landscapes of the savanna. Meanwhile, the carnivorous mammals that preyed on these herbivores evolved alongside them, leading to the development of specialized hunting strategies. Large cats, such as the saber-toothed tiger, evolved to hunt in packs and take down large prey, while other predators, such as early wolves, developed social structures that allowed them to work together to catch their quarry. These adaptations helped shape the complex food webs that would characterize terrestrial ecosystems for millions of years to come. From space, the Earth would have appeared as a planet of ever-changing landscapes. Vast stretches of green forests and grasslands would have been interspersed with deserts and savannas, while ice caps slowly grew at the poles. The planet was becoming increasingly hospitable to mammals, whose diversity continued to rise, filling nearly every available ecological niche. The rise of mammals during the Cenozoic era marked the beginning of a new age of life on Earth, one that would eventually lead to the emergence of human beings and the complex ecosystems we recognize today. The Age of Giants, a time marked by the evolution of enormous mammals, took place during the Pleistocene epoch, approximately 2.6 million to 700 years ago. This period was dominated by megafauna-massive creatures that roamed the Earth in a variety of environments. These colossal animals, many of which would be considered giants by today's standards, adapted to the cold, harsh climates of the Ice Ages. Their sizes and physical traits were products of the environmental conditions they faced, as well as the absence of large predators that could challenge them. As the planet entered a series of ice ages, the Earth's climate became colder, leading to the expansion of glaciers over much of the northern hemisphere. Vast stretches of tundra and steppe developed, providing ideal habitats for large herbivores. Grasslands covered the Earth's surface, and this rich, nutrient-dense environment supported the growth of large vegetation, which fueled the enormous herbivores that grazed the land. Mammals adapted to these conditions, evolving to become much larger than their predecessors. Megafauna were present on every continent during this period. In the northern latitudes, woolly mammoths and mastodons dominated the cold, icy landscapes. These creatures, with their thick fur and long curved tusks, were perfectly suited to the freezing conditions of the Pleistocene. Their bodies were massive, with adult males of the woolly mammoth weighing several tons. Their size was an adaptation to the cold, as larger bodies retained heat more effectively. In addition to their size, their tusks were used for foraging beneath the snow, as well as for defense against predators and rivals. At the same time, giant ground sloths roamed the forests and grasslands of North and South America. These herbivores, which could reach up to 20 feet in length, were some of the largest mammals to ever walk the Earth. Their slow movements were offset by their massive size, and they had few natural predators, as their enormous bulk made them difficult to hunt. They primarily fed on vegetation, using their long claws to pull down branches and trees to reach leaves high above the ground. In Australia, the megafauna were no less impressive. The giant wombat, a herbivore the size of a small car, and the diprotodon, a massive marsupial that resembled a giant wombat or a large bear, were common. These creatures, alongside enormous flightless birds like the mahirung, were well suited to the Australian environment. Their massive size helped them survive in an ecosystem where smaller creatures struggled against the challenges posed by the land's extreme temperatures. In Africa, the savannas were home to giant rhinoceroses and the largest terrestrial carnivore ever to live, the short-faced bear. These animals existed alongside the ancestors of modern elephants and buffalo. The African continent, with its diverse ecosystems, provided a range of environments for these giants to thrive, from open grasslands to dense forests. The oceans, too, were inhabited by giant creatures during the Pleistocene. The seas were filled with enormous whales and giant sharks. These ocean giants evolved in response to the abundant marine life that flourished during this time, making them some of the largest creatures ever to have lived on Earth. The giant sperm whale, which could reach lengths of over 60 feet, ruled the oceans, preying on giant squid and other deep-sea creatures. The oceans were a critical ecosystem during this time, as they supported a wide range of creatures, both large and small, that interacted within a delicate balance. The rise of megafauna was a result of the environmental conditions created by the Ice Ages. The cooler temperatures and the vast expanses of tundra allowed for the evolution of massive herbivores, which in turn supported the rise of larger predators. However, the end of the Pleistocene saw a rapid decline in these giant animals, a phenomenon that is still debated by scientists today. While climate change and human hunting played significant roles in the extinction of many megafauna species, it is clear that the combination of these factors led to a dramatic loss of biodiversity. As the climate warmed at the end of the Ice Ages, glaciers began to retreat, and the landscapes that had once been ideal for megafauna changed. Forests expanded, and the open grasslands that had sustained large herbivores began to shrink. The once abundant food sources for megafauna became scarcer, and many of these large creatures struggled to adapt to the changing environment. At the same time, human populations were increasing, and early humans, who had learned to hunt and use tools, began to target these massive animals for food and resources. Humans likely played a significant role in the extinction of many megafauna species. Archaeological evidence suggests that early humans hunted large animals such as mammoths and mastodons, possibly contributing to their population decline. The rise of more advanced hunting techniques, including the use of spears and traps, made humans more effective at capturing these giants. As human populations spread across the globe, the pressure on megafauna species increased, further driving their decline. The warming climate of the Holocene also contributed to the disappearance of megafauna. As temperatures rose, many of the cold-adapted species that had thrived during the ice ages were no longer able to survive. The changing ecosystems, combined with the growing presence of humans, led to the extinction of many of these giant animals. By the end of the Pleistocene, the age of megafauna had come to a close. Today, only a few remnants of this once great age remain. Modern elephants, rhinos, and hippos are the descendants of these ancient giants. While their sizes are much smaller than those of their prehistoric ancestors, they still embody the legacy of the megafauna that once roamed the Earth. The extinction of these animals marked a dramatic shift in the ecosystems of the planet, paving the way for the rise of smaller mammals and the eventual dominance of human civilizations. Looking back from space, Earth during the Pleistocene would have appeared as a land of vast, open plains and towering ice sheets. Large herds of herbivores would have dotted the landscape, while packs of carnivores hunted in the distance. The oceans would have been filled with giant creatures, and the skies above would have been dominated by enormous birds. It was a time of great diversity and complexity, a period when giants ruled the Earth. The Ice Ages, a series of long periods of global cooling, had profound effects on the Earth's ecosystems, shaping the landscapes, climates, and species that we know today. Spanning millions of years, these cold periods drastically altered the planet's surface, creating the conditions that led to the development of modern ecosystems and the eventual rise of human civilization. The Ice Ages, often referred to as the Pleistocene glaciation, began around 2.6 million years ago and lasted until approximately 700 years ago, influencing everything from the formation of glaciers to the evolution of species. As the Earth entered the Ice Ages, the planet's climate shifted, with average temperatures dropping significantly. Massive ice sheets spread across large portions of North America, Europe, and Asia, while other regions of the world, such as parts of Africa and Australia, experienced cooler, drier conditions. This cooling trend led to the expansion of tundra and steppe environments, where cold-adapted plants and animals could thrive. These environments became the primary habitats for many species, and the adaptations they developed would go on to shape the world in ways that are still visible today. During the Ice Ages, glacier shuge, slow-moving rivers of ice carved out vast portions of the landscape. As they advanced and retreated over thousands of years, glaciers shaped valleys, mountains, and fjords, leaving behind distinctive features that are still found in regions like Canada, Scandinavia, and the Alps. The glaciers also had a significant impact on the ocean levels, as large volumes of water were locked up in ice. This caused sea levels to drop, exposing large portions of the continental shelves and creating land bridges that allowed species to migrate between continents. In addition to the glaciers, the Ice Ages also brought about dramatic changes in the flora and fauna of the planet. Plants, which had evolved to survive in warm climates, were forced to adapt to the colder conditions. Some species, like the woolly mammoth, developed thick coats of fur to protect themselves from the harsh temperatures, while others, like the saber-toothed tiger, evolved larger bodies and stronger teeth to hunt and defend themselves in a cold, challenging environment. These adaptations allowed many species to thrive during the Ice Ages, but they also set the stage for future extinctions. As the planet warmed and the glaciers retreated, ecosystems changed again. Species that had evolved to survive in the cold Ice Age environments found themselves unable to adapt to the warming climate. The loss of habitat, combined with the arrival of human hunters, led to the extinction of many megafauna species, including the woolly mammoth, the giant ground sloth, and the saber-toothed tiger. But while the ice ages led to the extinction of many iconic species, they also provided the foundation for the ecosystems we know today. The cooling and warming cycles during the ice ages led to the formation of new biomes, such as tundra, temperate forests, and grasslands. The migration of species across land bridges connected different continents, leading to the exchange of genetic material and the evolution of new species. As the glaciers retreated, forests began to grow, and the plains and grasslands that had once supported giant herbivores were gradually replaced by modern ecosystems. The cooling and warming of the planet during the ice ages also had a lasting impact on plant life. In regions like North America and Europe, the retreating glaciers left behind fertile soils that would become the foundation for modern forests. As temperatures warmed, these areas were colonized by trees like pine, spruce, and birch, which would go on to form the dense forests that we associate with these regions today. These forests would provide habitat for a variety of species, from small mammals to large predators, and play a key role in shaping the biodiversity of the planet. Meanwhile, in the oceans, the ice ages also brought about significant changes. The lower sea levels exposed vast stretches of the continental shelves, creating new habitats for marine life. This led to the evolution of new species and the migration of marine creatures to new regions. As the ice ages ended and sea levels rose again, these new ecosystems were inundated, but their influence on oceanic biodiversity can still be seen in the marine species that inhabit the planet today. The end of the ice ages marked a significant turning point in the Earth's history. With the arrival of warmer temperatures, ecosystems began to transform once again. The vast ice sheets that had once covered much of the northern hemisphere began to melt, giving rise to new habitats for plants and animals. This warming trend brought about the rise of the modern climate zones that we are familiar with today, including tropical, temperate, and polar regions. The disappearance of the ice sheets also led to the rise of human civilization. As the climate warmed, humans began to migrate out of Africa and into other parts of the world, adapting to new environments and developing new technologies to survive. The end of the ice ages marked the beginning of the Holocene epoch, a period that saw the growth of agriculture, the domestication of animals, and the rise of complex societies. The ice ages, despite their dramatic changes, ultimately helped shape the Earth's ecosystems into the diverse and complex web of life that exists today. From the glaciers that carved the land to the warming temperatures that fostered new plant and animal species, the ice ages set the stage for the rise of modern ecosystems. While the extinction of many megafauna species marked the end of one era, it also paved the way for the development of ecosystems that continue to support life on Earth. The legacy of the ice ages is seen not only in the landforms and climate patterns of today, but also in the incredible diversity of species that call the planet home. As we look at the Earth from space today, we can see the lasting impact of the ice ages on the planet's surface. Vast, frozen tundras and the remnants of ancient glaciers still mark the regions that were once covered by ice, while the lush, green forests and grasslands of the temperate and tropical zones tell the story of a warmer world. The oceans, teeming with life, reflect the changes brought about by the ice ages, from the evolution of marine species to the shifting currents and sea levels. The ice ages, in all their grandeur and devastation, were a pivotal chapter in the history of life on Earth, shaping the planet in ways that are still visible to us today. The age of humans, which began roughly 300 years ago, marks a pivotal chapter in the history of Earth's ecosystems. Unlike any other species, humans have had a profound and lasting impact on the planet's landscapes, climates, and biodiversity. From the earliest hunter-gatherer societies to the rise of agricultural civilizations and modern industrialization, human activity has altered the course of natural history. This period is defined not only by the rise of human culture and technology, but also by the dramatic effects humans have had on the Earth's ecosystems and the extinction of numerous species. Early humans, or Homo sapiens, emerged in Africa and gradually spread across the globe, adapting to various environments and creating societies that interacted with their surroundings. These early humans were hunter-gatherers, relying on the natural resources around them for survival. They hunted large animals, gathered plant-based food, and created tools from stone and bone. Although their populations were small and their technology primitive compared to today, they still had an influence on the environment. As human populations grew, so did their impact on the ecosystems they inhabited. The spread of humans across continents brought with it the hunting of large megafauna, including mammoths, mastodons, and giant ground sloths. Archaeological evidence suggests that these early humans, with their tools and cooperative hunting strategies, played a significant role in the extinction of many of these giant species. While the exact causes of these extinctions are debated, it is likely that the combination of hunting pressure and climate change contributed to the collapse of many megafauna populations. The extinction of large species during the early human era was only the beginning. As humans developed more advanced tools and began to settle in permanent communities, they began to alter the environment on a larger scale. The development of agriculture, for instance, led to the clearing of forests and the draining of wetlands to make way for crops and livestock. This transformation of the landscape had profound effects on local ecosystems, disrupting the habitats of many species and leading to the decline of plant and animal populations. The domestication of animals further altered ecosystems, as humans selectively bred animals for specific traits, changing the genetics and behaviors of these species. The rise of agriculture also led to the creation of monocultures, where vast stretches of land were planted with a single type of crop, often at the expense of biodiversity. These agricultural practices, which began around 10,000 years ago, were the foundation of human civilization, but they also set the stage for significant ecological changes. With the advent of the Industrial Revolution around 200 years ago, human influence on the environment reached unprecedented levels. Industrialization brought about the mass production of goods, the widespread use of fossil fuels, and the creation of new technologies that enabled humans to modify the landscape on a global scale. Factories, cities, and transportation networks grew rapidly, resulting in large-scale deforestation, habitat destruction, and pollution. The burning of coal, oil, and gas released large amounts of carbon dioxide into the atmosphere, contributing to global warming and climate change. The Industrial Revolution also spurred the rapid expansion of human populations, which in turn led to increased demands for food, water, and other resources. The growth of cities, the rise of commercial agriculture, and the expansion of mining and drilling operations all contributed to the degradation of ecosystems. Forests were cleared for timber and farmland. Wetlands were drained for development, and rivers were dammed to provide water for cities and agriculture. One of the most significant impacts of human activity on ecosystems has been the loss of biodiversity. As habitats are destroyed and species are overexploited for food, medicine, and other resources, many species have gone extinct. The extinction rate has increased dramatically in recent centuries, with an estimated 1 million species currently at risk of extinction due to human activity. The main drivers of this extinction crisis include habitat destruction, pollution, climate change, overfishing, and the introduction of invasive species. The loss of biodiversity has far-reaching consequences for ecosystems. Every species plays a role in maintaining the balance of an ecosystem, and when species disappear, it can lead to the collapse of entire ecosystems. For example, the extinction of bees, which are critical pollinators for many crops, could lead to the collapse of food systems. Similarly, the loss of large predators, such as wolves or sharks, can disrupt the food chain and lead to the overpopulation of certain species, which in turn can harm plant life and other animals. Climate change, driven by the burning of fossil fuels and the release of greenhouse gases, is another major factor impacting ecosystems. As the planet warms, ecosystems are being forced to adapt. Many species are migrating to cooler regions or higher altitudes, but not all species can move fast enough to keep up with the changing climate. This has led to a phenomenon known as climate-driven extinction, where species that cannot adapt to the new conditions are disappearing. Some species are also facing changes in the timing of events like breeding, migration, and flowering, which disrupts their ability to survive. The effects of human activity on the planet are not limited to the loss of species and the disruption of ecosystems. Pollution has become a major environmental issue, with toxins from industrial waste, agricultural runoff, and plastics poisoning ecosystems around the world. Oceans are filled with plastic waste, which harms marine life, while air pollution from factories and vehicles contributes to respiratory illnesses and environmental degradation. The contamination of soil and water by chemicals has led to the degradation of agricultural land and the contamination of drinking water sources. Despite the widespread destruction caused by human activity, there are efforts underway to mitigate the damage and protect ecosystems. Conservation efforts, such as the creation of protected areas, wildlife corridors, and breeding programs, have helped to save some species from extinction. Sustainable agriculture, which focuses on practices that minimize environmental damage, is gaining traction as an alternative to industrial farming. The shift towards renewable energy sources, such as wind, solar, and hydroelectric power, aims to reduce the reliance on fossil fuels and curb climate change. The concept of rewilding, restoring ecosystems to their natural state by reintroducing extinct or endangered species, has also gained attention in recent years. Efforts to reintroduce species like wolves, bison, and even the woolly mammoth, through genetic engineering, are being explored as ways to restore ecological balance and improve biodiversity. As we look at the planet from space, it is clear that humans have had a profound effect on the Earth's ecosystems. Vast stretches of land have been transformed for agriculture, industry, and urban development, while the effects of climate change are visible in the warming of the oceans, shrinking ice caps, and increased frequency of extreme weather events. Despite the damage done, the resilience of the planet's ecosystems is evident. Many species are adapting to new conditions, and efforts to protect and restore ecosystems are ongoing. The age of humans has undeniably altered the course of Earth's history, but it is not too late to reverse some of the damage. By focusing on conservation, sustainability, and restoration, humans can help protect the planet's ecosystems and ensure that future generations inherit a world teeming with life. As we look to the future, the fate of Earth's ecosystems hangs in the balance. The planet's ecosystems, which have evolved over millions of years, face unprecedented challenges. Human activity has already had profound effects on these ecosystems, but the next few decades will be crucial in determining whether they can recover or whether we will face even greater environmental crises. The future of Earth's ecosystems will depend on the choices we make today. One of the most pressing challenges is climate change. The Earth's average temperature is rising due to the increasing concentration of greenhouse gases in the atmosphere, primarily carbon dioxide from burning fossil fuels. This warming is already having significant effects on ecosystems, from melting polar ice caps and glaciers to shifting weather patterns and more frequent extreme weather events. The future of ecosystems will depend on how quickly we can reduce greenhouse gas emissions and mitigate the effects of climate change. As the planet warms, ecosystems will continue to shift. Species will be forced to migrate to cooler regions or higher altitudes, but many will not be able to move fast enough to adapt to the changing climate. This could lead to a dramatic loss of biodiversity, as species that are unable to adapt or relocate face extinction. Ecosystems that are already under stress, such as coral reefs and rainforests, will be particularly vulnerable to the impacts of climate change. The loss of biodiversity, already at an all-time high due to habitat destruction, pollution, and overexploitation, is another major challenge for the future. Ecosystems rely on the intricate web of relationships between species, and the loss of even a single species can have ripple effects throughout the ecosystem. As species go extinct, ecosystems become less resilient and more vulnerable to collapse. Preserving biodiversity will be crucial for the health and stability of ecosystems in the future. Pollution is another significant challenge that will shape the future of ecosystems. Industrial pollution, agricultural runoff, and plastic waste continue to contaminate the air, water, and soil. In the coming decades, efforts to reduce pollution will be vital for protecting ecosystems. Cleaner technologies, sustainable agricultural practices, and better waste management systems will be necessary to reduce the impact of pollution on ecosystems. However, there are also opportunities for restoring and protecting ecosystems. Despite the many challenges, the resilience of nature is remarkable, and there are numerous efforts underway to protect and restore ecosystems. Conservation efforts have made significant progress in recent years, with the establishment of protected areas, wildlife corridors, and sustainable land use practices. Many endangered species have been saved from extinction through conservation programs, and efforts to restore degraded ecosystems, such as reforestation projects and wetland restoration, are gaining momentum. One promising avenue for restoring ecosystems is the concept of rewilding. Rewilding involves restoring ecosystems to their natural state by reintroducing species that have been lost due to human activity. This can include reintroducing large predators, such as wolves and bears, or herbivores like bison and wild horses. Rewilding has shown promising results in some areas, with ecosystems becoming more balanced and resilient as a result. In the future, rewilding could play a key role in restoring ecosystems and promoting biodiversity. Another opportunity lies in the development of sustainable technologies. As renewable energy sources like wind, solar, and hydroelectric power become more widespread, the reliance on fossil fuels can decrease, reducing the impact of climate change. Sustainable agriculture, which focuses on reducing environmental harm, could also play a key role in the future of ecosystems. Practices like agroforestry, organic farming, and regenerative agriculture can help restore soil health, reduce pollution, and increase biodiversity on farmlands. There is also potential for innovation in technology and science that could help us address environmental challenges. For example, advances in biotechnology could allow for the restoration of ecosystems through genetic engineering, such as the reintroduction of extinct species or the modification of species to be more resilient to climate change. Artificial intelligence and data analysis could help us monitor ecosystems more effectively, enabling faster responses to threats like invasive species or habitat loss. The future of Earth's ecosystems will also depend on the actions of governments, businesses, and individuals. Global cooperation will be essential in addressing environmental challenges. International agreements like the Paris Agreement on Climate Change represent important steps toward reducing greenhouse gas emissions and limiting global warming. Governments can also play a key role in regulating pollution, protecting biodiversity, and investing in conservation programs. Businesses will need to embrace sustainable practices and take responsibility for their environmental impact. The transition to a circular economy, where resources are reused and waste is minimized, will be essential in reducing the strain on ecosystems. Companies that prioritize sustainability will help pave the way for a more sustainable future. Individuals also have a role to play. Through lifestyle choices, such as reducing consumption, supporting sustainable products, and advocating for environmental policies, people can contribute to the preservation of ecosystems. Small actions, when taken by millions of individuals, can have a significant collective impact on the environment. As we move into the future, it is clear that the challenges facing Earth's ecosystems are immense. However, there is hope. Through concerted efforts to address climate change, reduce pollution, conserve biodiversity, and restore ecosystems, it is possible to create a more sustainable future for the planet. The resilience of nature and the creativity of humans will be key in shaping the future of Earth's ecosystems. By working together, we can ensure that the planet's ecosystems continue to thrive, providing essential services for generations to come. As we stand at the crossroads of environmental transformation, humanity's role in shaping the future of Earth's ecosystems has never been more critical. Our influence, once limited to localized regions, has expanded across the globe, altering landscapes, oceans, and climates. The power to destroy has been matched only by our potential to restore. The choices we make today will determine the health and stability of the ecosystems that sustain life on Earth, not just for ourselves, but for countless other species that share the planet. The future of ecosystems is largely in our hands. While human activity has caused unprecedented damage to the environment, humans also possess the ability to enact positive change. The key question is whether we can shift our mindset from exploitation and consumption to stewardship and sustainability. Humanity's role will not only be to curb destructive practices, but also to foster regeneration and resilience in the face of ongoing environmental challenges. Ecosystem conservation and protection. The protection of ecosystems from further degradation is one of the most immediate actions humanity must take. Ecosystems, from forests and wetlands to oceans and grasslands, are the life support systems of the planet. They regulate the climate, purify water, provide food and medicine, and support biodiversity. However, these systems are under threat from deforestation, urbanization, industrial pollution, and agricultural expansion. Unless we take urgent action to protect and conserve these areas, we risk losing the very resources that sustain life. One of the most effective ways to protect ecosystems is through the establishment of protected areas, such as national parks, wildlife reserves, and marine protected areas. These spaces allow ecosystems to function without the constant pressure of human development. Global conservation initiatives, such as the United Nations Convention on Biological Diversity, have worked to establish protected areas and conserve wildlife. However, only a fraction of the planet's ecosystems are currently protected. Expanding and strengthening these protected areas, as well as improving enforcement, will be crucial for safeguarding the future of ecosystems. Another key aspect of ecosystem protection is addressing the drivers of habitat destruction. Urban sprawl, agriculture, and mining continue to threaten critical ecosystems. Sustainable land use practices, such as agroforestry, sustainable forestry, and eco-friendly agriculture, can help to balance human needs with ecosystem preservation. This shift to more sustainable practices not only protects biodiversity, but also enhances the resilience of ecosystems to climate change. Restoration and regeneration. While protecting existing ecosystems is vital, restoring degraded ecosystems is equally important. Over the centuries, vast tracts of land, rivers, and oceans have been damaged by human activity. Forests have been cleared, wetlands drained, and coral reefs destroyed. The restoration of these ecosystems is essential to rebuilding biodiversity and improving ecosystem services. The restoration of ecosystems can take many forms, from reforestation and wetland restoration to the rehabilitation of degraded soils and the removal of invasive species. Reforestation, for example, is one of the most effective ways to combat climate change. Trees not only sequester carbon, but also provide habitats for countless species, regulate water cycles, and help prevent soil erosion. Similar efforts to restore wetlands and grasslands can improve water quality, reduce flooding, and enhance biodiversity. Recovery is not limited to land-based ecosystems. The oceans, which cover more than 70% of the planet's surface, are home to some of the most diverse ecosystems on Earth. Coral reefs, often referred to as the rainforests of the sea, are some of the most biodiverse ecosystems in the world, but are also among the most threatened. Coral bleaching, caused by rising sea temperatures, and ocean acidification, caused by increased carbon dioxide levels, are destroying coral reefs at alarming rates. Efforts to restore coral reefs through coral planting and marine protected areas are crucial for preserving ocean biodiversity and protecting the livelihoods of millions of people who depend on these ecosystems for food and income. Climate change mitigation. Addressing climate change is perhaps the most significant challenge humanity faces in preserving Earth's ecosystems. Climate change affects ecosystems on a global scale, altering weather patterns, sea levels, and ecosystems' ability to function. Reducing the impact of climate change is essential not only for the health of ecosystems but also for the survival of the species that rely on them, including humans. Humanity's role in mitigating climate change is clear. We must reduce greenhouse gas emissions, transition to renewable energy, and shift to more sustainable practices in every sector of society. This requires collective action across nations, industries, and individuals. International agreements, such as the Paris Agreement, provide a framework for reducing emissions and limiting global temperature rise. Governments must implement policies that encourage the adoption of clean energy technologies, energy efficiency, and carbon capture and storage. Individual actions also matter. Transitioning to sustainable lifestyles, reducing waste, supporting sustainable agriculture, and adopting low-carbon technologies can all contribute to mitigating climate change. The transition to a circular economy, where resources are reused, recycled, and sustainably sourced, will also reduce the pressure on ecosystems and lessen environmental degradation. Biodiversity preservation and genetic conservation. Preserving biodiversity, the variety of life on Earth, is essential to maintaining healthy ecosystems. Every species, no matter how small, plays a role in the functioning of ecosystems, from pollinators that ensure the reproduction of plants to apex predators that regulate prey populations. The loss of biodiversity weakens ecosystems and makes them more vulnerable to collapse. This is why protecting endangered species and promoting biodiversity conservation is a key aspect of humanity's role in safeguarding ecosystems. In addition to protecting species in the wild, genetic conservation is becoming increasingly important. Advances in biotechnology and genomics have allowed for the collection and preservation of genetic material from endangered species, which can be used to help repopulate species that are at risk of extinction. Gene banks and seed banks are also being established to protect the genetic diversity of plants and animals for future generations. This technology, along with efforts to combat poaching and illegal trade, can play a pivotal role in preserving biodiversity. Education and advocacy. Humanity's role in shaping the future of Earth's ecosystems is not just about policies, technologies, and restoration efforts. Education and advocacy are also vital. Raising awareness about the importance of ecosystems and the threats they face can inspire individuals, communities, and governments to take action. Environmental education empowers people to make informed choices about how they interact with the planet, from reducing waste to supporting sustainable businesses. Advocacy plays a key role in pushing for policies that protect ecosystems. Environmental organizations and grassroots movements have been instrumental in advocating for stronger environmental protections, more funding for conservation, and policies that address climate change. As public awareness of environmental issues grows, so does the political pressure to implement change. Collectively, these efforts can drive the systemic change needed to protect and restore ecosystems. The path forward. As we look to the future, humanity's role in shaping Earth's ecosystems will be defined by our ability to act. The challenges are immense, but the opportunities are just as great. Through conservation, restoration, climate action, and biodiversity preservation, we can safeguard the health of the planet for future generations. While the road ahead may be difficult, humanity has the knowledge, technology, and creativity to rise to the challenge. The question is not whether we can create a better future for ecosystems, but whether we have the will to do so. The future of Earth's ecosystems depends on the choices we make today. Will we continue on a path of destruction, or will we embrace our role as stewards of the planet? The future of life on Earth rests in our hands. Technology has the potential to be one of the most powerful tools in the fight, to preserve and restore Earth's ecosystems. While human activity has led to significant environmental degradation, technological advancements are also paving the way for more sustainable practices and the restoration of ecosystems. From artificial intelligence to renewable energy and biotechnology, technology offers innovative solutions to the challenges facing our planet's ecosystems. Monitoring and data collection. One of the critical roles technology can play in ecosystem preservation is through monitoring and data collection. Understanding the health of ecosystems is essential for taking effective action. Modern technology allows for the collection and analysis of large amounts of environmental data, enabling scientists to monitor ecosystems on a global scale in real time. Satellite technology, for example, has revolutionized our ability to track deforestation, monitor changes in land use, and observe shifts in the climate. Satellites can provide data on temperature changes, forest cover, and even the movement of wildlife, which can help inform conservation efforts. In addition, sensors placed in forests, oceans, and other ecosystems can provide continuous data on environmental conditions, enabling rapid responses to environmental changes. Drones are another valuable tool for monitoring ecosystems. They can be used to survey large and remote areas, such as forests and coral reefs, and provide high-resolution images that are difficult to obtain using traditional methods. Drones can help scientists track changes in biodiversity, assess the health of ecosystems, and monitor conservation efforts. They are also useful in areas where it is difficult or dangerous to send human researchers. Artificial intelligence, AI, plays a key role in processing and analyzing the vast amounts of data collected from satellites, drones, and sensors. AI algorithms can identify patterns, predict future environmental changes, and assess the effectiveness of conservation strategies. This ability to quickly process and analyze data is invaluable in responding to environmental threats in a timely manner. Renewable energy. Transitioning to renewable energy is one of the most important technological solutions for mitigating the effects of climate change and protecting ecosystems. The burning of fossil fuels for energy is a major contributor to greenhouse gas emissions, which are driving global warming and disrupting ecosystems. Renewable energy sources, such as solar, wind, and hydroelectric power, provide a cleaner alternative that can significantly reduce our environmental footprint. Solar power, for example, has seen rapid technological advancements in recent years, making it more affordable and efficient. Solar panels are now able to generate more energy from less sunlight, and new innovations, such as solar farms and solar windows, are expanding the potential for solar energy to replace fossil fuels. Similarly, wind energy has become a major player in the renewable energy sector, with wind turbines becoming more efficient and cost-effective. Another promising renewable energy source is geothermal energy, which harnesses heat from the Earth's core to generate electricity. Geothermal power plants have the potential to provide a continuous and reliable source of energy without emitting harmful greenhouse gases. Hydropower, which uses the movement of water to generate electricity, remains a critical source of renewable energy in many parts of the world, though care must be taken to ensure that it does not negatively impact aquatic ecosystems. As renewable energy sources continue to evolve, they will play a crucial role in reducing our reliance on fossil fuels and protecting ecosystems from the harmful effects of climate change. Biotechnology and genetic engineering. Biotechnology and genetic engineering offer innovative solutions to some of the most pressing environmental challenges. Genetic modification techniques can help create more resilient crops that require fewer pesticides, conserve water, and withstand the effects of climate change. Genetically modified organisms, GMOs, have already been developed to increase crop yields and improve the nutritional value of food, and further advancements in this field could help address food security concerns while reducing environmental impact. In addition to agriculture, biotechnology is being used to restore ecosystems and mitigate environmental damage. One such example is the use of genetically engineered bacteria and fungi to clean up polluted environments. These organisms can break down toxins and pollutants, such as oil spills, heavy metals, and plastics, effectively removing harmful substances from the environment. Genetic engineering is also being explored as a tool for conserving endangered species. In some cases, scientists are working to edit the genes of endangered species to make them more resilient to environmental changes, such as disease or climate fluctuations. While controversial, these technologies could offer a last resort option for saving species on the brink of extinction. Precision agriculture. Agriculture is one of the primary drivers of environmental degradation, with practices such as deforestation, pesticide use, and overgrazing contributing to habitat loss and biodiversity decline. However, technological advancements in agriculture are offering new ways to produce food more sustainably and minimize environmental harm. Precision agriculture, which uses technology to monitor and manage crops with high accuracy, is one of the most promising approaches. By using GPS, drones, and sensors, farmers can monitor soil health, weather patterns, and crop growth in real time. This data allows farmers to apply fertilizers, water, and pesticides only when and where they are needed, reducing waste and minimizing environmental impact. Precision agriculture also helps optimize crop yields, ensuring that food production can meet the demands of a growing global population without further degrading ecosystems. In addition to precision agriculture, vertical farming is another innovative agricultural technology that could help reduce the environmental footprint of food production. Vertical farms use hydroponic or aeroponic systems to grow crops in stacked layers, often in urban areas, reducing the need for large agricultural plots and minimizing water usage. These farms can produce food with significantly less land and water, while also reducing transportation emissions by growing food closer to where it will be consumed. Eco-friendly materials and circular economy. As humanity moves toward a more sustainable future, the development of eco-friendly materials will play an important role in preserving ecosystems. Traditional materials, such as plastic, metal, and concrete, are often resource-intensive to produce and harmful to the environment when discarded. New materials, such as biodegradable plastics, plant-based alternatives, and recycled materials, offer more sustainable options for manufacturing and construction. In particular, the circular economy, which focuses on reusing, recycling, and repurposing materials, has gained traction as a strategy for reducing waste and minimizing resource extraction. Instead of following a linear model of take, make, dispose, the circular economy seeks to keep materials in use for as long as possible, reducing the need for raw materials and lowering the environmental impact of production. Advances in recycling technology are also contributing to the growth of the circular economy. New processes allow for more efficient recycling of materials like plastics and metals, turning waste into valuable resources that can be used to produce new products. In addition, upcycling, which involves converting waste materials into higher value products, is gaining popularity as a way to reduce environmental impact and promote sustainability. The future of environmental technology. The role of technology in preserving Earth's ecosystems is still evolving, with many exciting developments on the horizon. From autonomous vehicles and drones to advancements in nanotechnology and artificial intelligence, new technologies will continue to shape the way we interact with the planet. As technology evolves, it will become increasingly important to ensure that these advancements are used responsibly and ethically to protect and restore ecosystems. One area of growth is the use of artificial intelligence in environmental monitoring and decision-making. AI can help optimize resource use, predict environmental changes, and automate conservation efforts, making it an invaluable tool in ecosystem management. For example, AI can be used to track wildlife populations, identify threats to ecosystems, and even develop new conservation strategies based on data analysis. The future of environmental technology will also see the development of new, more efficient, renewable energy sources. Innovations in energy storage, such as advanced batteries and grid systems, will make renewable energy more reliable and accessible. This will help reduce our dependence on fossil fuels and ease the transition to a low-carbon future. As technology continues to evolve, humanity will be better equipped to tackle the challenges facing Earth's ecosystems. While the road ahead will not be easy, the potential of technology to drive positive environmental change offers hope for a more sustainable and resilient future. Climate change has had profound effects on Earth's ecosystems throughout history, influencing the composition of species, the structure of environments, and the planet's overall habitability. While the current climate crisis is a modern phenomenon, prehistoric climate shifts offer valuable insights into how ecosystems respond to extreme changes in temperature, atmospheric composition, and sea levels. These shifts were key factors in shaping the evolution of life on Earth, with major climatic events often preceding mass extinctions that forever altered the planet's biodiversity. The Paleozoic era. The earliest signs of climate change, the Paleozoic era, spanning from roughly 541 to 252 million years ago, saw some of the most dramatic changes in Earth's climate and ecosystems. During this time, the planet experienced several ice ages, as well as periods of intense global warming. These climatic fluctuations played a crucial role in shaping the ecosystems of the era. Early in the Paleozoic, Earth's continents were positioned in a way that allowed for massive glaciations. The late Ordovician, about 445 million years ago, was marked by a major ice age, which caused a significant drop in sea levels and a shift in atmospheric conditions. The cooling of the planet reduced the habitable area for many species, particularly marine life, leading to one of the largest mass extinctions in Earth's history, the Ordovician-Silurian extinction event. Nearly 85% of marine species were wiped out, and ecosystems that had thrived in warmer waters disappeared. After this ice age, the planet warmed significantly during the Silurian and Devonian periods. This warming led to the formation of lush, carbon-rich forests, and the diversification of life, particularly terrestrial plants and early land-dwelling animals. However, the warmer conditions also set the stage for further ecological changes, including fluctuations in atmospheric oxygen levels, which played a role in the extinction of certain species and the rise of new ones. The Mesozoic era, the age of the dinosaurs and climate extremes. The Mesozoic era, often referred to as the Age of the Dinosaurs, was a period of significant climate change that saw Earth's ecosystems evolve into the rich, diverse landscapes that we associate with dinosaurs and other prehistoric creatures. During the Triassic, Jurassic, and Cretaceous periods, the planet's climate was generally warmer and more stable than today, but it was also marked by periodic extremes that influenced both plant and animal life. Early in the Mesozoic, the planet's climate was much warmer than it is now. The Middle Triassic, around 230 million years ago, was a time of relatively stable temperatures and high atmospheric carbon dioxide levels. This warm climate allowed dinosaurs to flourish, and early plants adapted to these conditions by evolving into the vast forests of conifers, cycads, and ferns that dominated the landscape. However, throughout the Mesozoic, the Earth also experienced major shifts in climate. One of the most significant was the late Jurassic period, around 150 million years ago, when global temperatures began to rise even further. This warm phase was accompanied by increased volcanic activity, which released large amounts of carbon dioxide and other greenhouse gases into the atmosphere, exacerbating global warming. This period saw the rapid diversification of dinosaurs and the rise of massive herbivores and predators, such as the sauropods and theropods, as well as the appearance of the first birds. The Cretaceous period, around 100 million years ago, was marked by even higher temperatures, creating a greenhouse Earth climate. The polar regions were much warmer, and sea levels were higher than they are today. These warm conditions fostered the development of diverse ecosystems, including tropical forests, vast seas teeming with life, and extensive coral reefs. However, this period of warmth also brought environmental stress to some species. As temperatures rose and ecosystems shifted, some species struggled to adapt, leading to local extinctions and shifts in biodiversity. The Paleocene-Eocene Thermal Maximum, PETM, a prehistoric climate crisis. Around 55 million years ago, during the transition from the Cretaceous to the Tertiary periods, Earth experienced one of the most extreme climate events in its history. The Paleocene-Eocene Thermal Maximum, PETM. This period was marked by a rapid increase in global temperatures, likely caused by massive amounts of carbon released into the atmosphere, possibly due to volcanic activity, methane hydrates, or the release of carbon from oceanic reservoirs. During the PETM, temperatures rose by as much as 5 to 8 degrees Celsius over a relatively short period of time, around 10 years, a rate of change that far exceeds the current pace of global warming. This dramatic warming event led to widespread disruptions in ecosystems, causing a shift in the distribution of plant and animal species. Tropical plants migrated to higher latitudes, and many species of cold-adapted organisms were pushed to extinction. Marine ecosystems were also significantly affected. The warming of the oceans led to decreased oxygen levels, which caused a mass extinction event in marine life. Many species of deep-sea organisms, including foraminifera, plankton, and fish, disappeared during this time, disrupting the marine food chain and altering oceanic ecosystems for millions of years. While the PETM was an event that occurred in the distant past, it provides a chilling preview of the potential effects of modern climate change. The rapid rate of warming during this period offers insight into how ecosystems might respond to the ongoing rise in global temperatures due to human activities. The role of climate change in the extinction of the dinosaurs, perhaps the most well-known instance of climate change causing widespread ecological disruption, occurred at the end of the Cretaceous period, around 66 million years ago, when a catastrophic event, believed to be a massive asteroid impact, led to the mass extinction of the dinosaurs. However, climate change likely played a role in the ecological turmoil that set the stage for this event. In the final stages of the Cretaceous, the planet was already undergoing significant climate fluctuations, including rising sea levels, changing temperatures, and shifting ecosystems. These changes put considerable stress on ecosystems, particularly in the marine environment, where many species of marine reptiles and ammonites were already struggling to adapt. The impact event, which created a global firestorm and a nuclear winter effect, may have pushed these ecosystems beyond their breaking point. In the aftermath of the asteroid impact, the planet entered a dark period, where dust and soot from the impact blocked out sunlight, causing global temperatures to plummet and disrupting photosynthesis. This climate shift would have decimated plant life, disrupting food chains and leading to the extinction of many species, including the dinosaurs. While the asteroid impact is the primary cause of the extinction event, the preceding climate changes would have weakened ecosystems, making it more difficult for many species to survive the harsh post-impact conditions. Climate change and modern ecosystems. A historical parallel. The climate change events of prehistoric Earth offer important lessons for understanding the potential impact of current human-induced climate change on ecosystems. While modern climate change is occurring at a much faster pace than the prehistoric climate shifts, the general patterns of ecosystem, disruption species, extinctions, habitat loss, and changes in biodiversity mirror those seen in the past. Today, human activity, such as burning fossil fuels, deforestation, and industrial agriculture, is releasing unprecedented amounts of greenhouse gases into the atmosphere, causing global temperatures to rise at an alarming rate. This rapid warming is already leading to shifts in ecosystems, with some species struggling to adapt to the changing conditions. The polar regions are warming faster than the rest of the planet, causing ice sheets to melt, while ecosystems in the tropics are facing stress from rising temperatures and deforestation. Climate change is also leading to ocean acidification, a process that is similar to the disruptions seen during the PETM, where increasing levels of carbon dioxide in the atmosphere are absorbed by the oceans, leading to a decrease in ocean pH levels. This is having a devastating impact on marine ecosystems, particularly coral reefs and shelled organisms, which are vital to the health of oceanic food chains. The lessons from prehistoric climate change remind us of the fragility of Earth's ecosystems in the face of rapid environmental shifts. While the planet has always experienced climate fluctuations, the unprecedented rate of change caused by human activities presents a unique challenge for ecosystems to adapt. Prehistoric plants played a central role in shaping Earth's ecosystems, influencing both the physical landscape and the development of animal life. From the first appearance of land plants to the massive forests of the Carboniferous period, plants were not only the foundation of most ecosystems but also the driving force behind the evolution of complex ecological relationships. In this section, we explore how plant life evolved throughout the prehistoric eras and how it shaped the ecosystems of the past. The rise of land plants in the Ordovician period. The first land plants began to appear around 475 million years ago, during the Ordovician period, marking a significant step in the evolution of life on Earth. These early plants were simple, non-vascular organisms that relied on water for reproduction and nutrient transport. They were small, moss-like plants that grew in moist, shaded environments. Their presence would have dramatically altered the landscape by stabilizing soil, preventing erosion, and providing new habitats for other organisms. The appearance of land plants had profound effects on the climate. As plants began to photosynthesize, they absorbed carbon dioxide from the atmosphere and released oxygen, slowly increasing oxygen levels and altering the planet's atmosphere. This process set the stage for the evolution of more complex life forms, including the eventual rise of animals that could breathe air. The Devonian period, the age of ferns, and the first forests. The Devonian period, around 400 million years ago, is often referred to as the Age of Ferns because of the widespread dominance of these plants during this time. During the early Devonian, plants began to evolve vascular tissues that allowed them to grow taller and more complex. This development was crucial for the expansion of terrestrial plant life, as it allowed plants to access more sunlight and nutrients from the soil, enabling them to grow larger and colonize a wider variety of environments. By the middle of the Devonian, the first true forests began to take shape. These early forests were dominated by ferns, horsetails, and lycopods, which grew alongside the first tree-like plants, such as the giant club mosses and seedless plants. These forests were not only large but also diverse, with a wide range of plant species occupying different niches in the ecosystem. The spread of these early forests had far-reaching effects on the planet's climate and ecosystems. As plant life expanded, it contributed to the formation of vast peat bogs, which eventually formed the coal deposits that would become so important in the Carboniferous period. The increase in plant biomass also helped to lower atmospheric carbon dioxide levels, contributing to the cooling of the planet and the formation of ice caps. The Carboniferous period. The rise of towering trees and coal swamps. The Carboniferous period, which lasted from approximately 359 to 299 million years ago, was a time of extraordinary plant growth. During this period, the Earth's climate was warm and humid, providing ideal conditions for the growth of vast forests. Towering trees, some of which grew over 30 meters tall, dominated the landscape. The Carboniferous period is also when some of the largest and most diverse plant species evolved, including tree ferns, club mosses, and the first seed plants. The lush, dense forests of the Carboniferous period were a crucial part of the planet's ecosystem. The dense plant life provided a stable environment for a variety of animals, including the first amphibians and insects. The development of large plants also had a significant impact on Earth's atmosphere, as these forests absorbed vast amounts of carbon dioxide, leading to a reduction in greenhouse gases and contributing to a cooler climate. The Carboniferous period was also a time of dramatic changes in the Earth's oceans. The increased burial of plant material in the soil led to the formation of massive peat bogs, which over millions of years would eventually transform into the coal deposits that fuel modern industry. This process also had a significant impact on the planet's carbon cycle, helping to regulate atmospheric temperatures and influence the global climate. The Permian period, the transition to a drier world. The Permian period, which occurred between 299 and 252 million years ago, marked the end of the Carboniferous and the beginning of a new era of plant evolution. During the early Permian, the Earth's climate began to shift toward drier and more variable conditions. The large, swampy forests that had dominated the Carboniferous period began to shrink as the planet became more arid. In their place, deserts and savanna-like environments began to spread. This change in climate had a profound impact on the plant life of the Permian period. The lush, swampy forests of the past gave way to drought-resistant plants, including the first conifers, cycads, and ginkgos. These plants were better adapted to the drier conditions and could survive in environments with less water. Their appearance marked the beginning of the modern plant world, as many of these groups would go on to dominate ecosystems in the Mesozoic era. The transition to a drier world during the Permian period also contributed to the mass extinction event at the end of the period. The changing climate and the loss of habitats for many species of plants and animals led to a significant decline in biodiversity, culminating in the Permian-Triassic extinction event, the largest mass extinction in Earth's history. The Mesozoic era, the age of gymnosperms and flowering plants. The Mesozoic era, known as the Age of the Dinosaurs, was also a time of great plant evolution. During this period, the planet's ecosystems were dominated by gymnosperms, non-flowering seed plants, such as conifers and cycads, which formed the bulk of the planet's forests. These plants thrived in the warm, dry conditions of the Mesozoic, and their seeds allowed them to survive in a variety of environments. However, the Mesozoic era also saw the appearance of the first flowering plants, or angiosperms, which would go on to revolutionize plant life. The appearance of flowering plants allowed for more efficient pollination and the development of diverse, fruit-bearing plants, providing new sources of food for animals. These plants quickly spread throughout the world, eventually becoming the dominant plant form by the end of the Cretaceous period. The impact of plants on prehistoric ecosystems. Plants were not only essential for the creation of oxygen-rich atmospheres, but also for the formation of ecosystems that could support diverse animal life. The development of plant life provided food, shelter, and habitats for a wide range of organisms. Plants also influenced the structure of ecosystems by creating different types of environments, from dense forests to open plains, that provided unique opportunities for evolution. As plants evolved, they interacted with other life forms in increasingly complex ways. The development of flowers and seeds allowed plants to form mutually beneficial relationships with animals, such as pollination and seed dispersal. These interactions helped to shape both plant and animal communities, and were key drivers of evolutionary change. The structure of plant life also influenced the climate. Through processes such as photosynthesis and the burial of carbon in soils, plants played a crucial role in regulating Earth's temperature and maintaining a stable climate. The large carbon-rich forests of the Carboniferous period helped to lower atmospheric carbon dioxide levels, contributing to the cooling of the planet. Similarly, the evolution of drought-resistant plants during the Permian period helped to stabilize ecosystems during a time of climatic change. Modern implications of prehistoric plant evolution. Understanding the evolution of prehistoric plants and their role in shaping Earth's ecosystems is essential for understanding the planet's current climate and biodiversity crisis. The lessons of the past can help us predict how modern plants might respond to current environmental challenges, such as climate change, habitat destruction, and invasive species. Today, plants continue to play a critical role in regulating the planet's climate by absorbing carbon dioxide and producing oxygen. However, human activities, such as deforestation and pollution, are disrupting these vital processes. Learning from the past and understanding the relationships between plants and climate can help inform strategies to preserve and protect the ecosystems that are vital for the future of life on Earth. The prehistoric oceans were vast, dynamic, and teeming with life long before the first land-dwelling animals ventured out of the sea. Oceans have always been the lifeblood of our planet, and the ecosystems they hosted were crucial to the development of life on Earth. In this section, we'll explore the evolution of prehistoric ocean ecosystems, from their origins in the earliest eons of life on Earth, through the age of massive marine reptiles, to the oceans of today. The Cambrian explosion, the birth of complex marine life. Around 541 million years ago, during the Cambrian period, the oceans underwent a dramatic transformation. This time, known as the Cambrian explosion, marked the sudden appearance of a vast array of complex, multicellular life forms. Prior to this, life in the oceans consisted mostly of simple, single-celled organisms. However, during the Cambrian explosion, marine ecosystems became populated with an incredible diversity of life, including the first arthropods, mollusks, and early vertebrates. The Cambrian seas were dominated by strange, armored creatures such as trilobites, which scuttled along the ocean floor, and the first predatory animals that hunted in the depths. The development of hard shells and exoskeletons provided protection from predators, and the oceans began to teem with life forms that exhibited the beginnings of many of the major animal groups that would evolve over the next hundreds of millions of years. The explosion of life in the oceans was driven by a combination of factors, including an increase in oxygen levels, the diversification of ecological niches, and the evolution of new forms of locomotion and feeding strategies. The Cambrian period laid the groundwork for the complex ecosystems that would follow, establishing the oceans as the center of life on Earth for millions of years to come. The Devonian seas, the rise of fish, and the first vertebrates. As the Devonian period unfolded, the oceans saw the rise of the first true vertebrates. Fish, which had evolved from early chordates, became the dominant organisms in the sea. These fish were highly diverse, ranging from the armored placoderm fish to the first cartilaginous sharks. The Devonian seas were a bustling world of marine life, with fish swimming through vast kelp forests, alongside the first true corals and early marine plants. By the late Devonian, some fish species had evolved the ability to survive in shallow coastal waters, where they began to venture onto land. This marked the beginning of a long and gradual transition from aquatic to terrestrial life, ultimately leading to the evolution of amphibians and land-dwelling vertebrates. The Permian seas, a world of strange marine life. The Permian period, which spanned from 299 to 252 million years ago, was marked by a diversification of marine life, particularly in the oceans. During this time, the seas were populated by large predatory fish, including the bizarre, long-snouted fish known as the coelacanths, and the strange, eel-like creatures known as placoderms. The oceans were also home to the first marine reptiles, including the ancestors of modern crocodiles and sea turtles. The Permian oceans were much warmer and more oxygenated than today's oceans, providing an ideal environment for the evolution of large marine reptiles. These reptiles flourished in the seas, dominating the food chain and contributing to the complexity of marine ecosystems. However, the Permian period ended with the largest mass extinction event in Earth's history, which wiped out nearly 90% of marine species. The oceans were left eerily quiet as life began to recover in the aftermath of this devastating event. The Mesozoic seas, the age of marine reptiles. The Mesozoic era, often called the Age of Dinosaurs, was also the age of marine reptiles. This era saw the rise of iconic marine reptiles, such as the ichthyosaurs, plesiosaurs, and mosasaurs, which dominated the seas for much of the era. These animals evolved from land-dwelling reptiles that returned to the ocean, adapting to life in the water with streamlined bodies, flippers, and long, powerful tails. The oceans of the Mesozoic were teeming with life. Coral reefs began to take shape, offering shelter and food for an array of marine creatures. Plankton flourished in the warm, shallow waters, supporting large populations of fish and providing food for larger marine predators. The Mesozoic seas were a rich and diverse environment where the food web was complex and dynamic, with marine reptiles sitting at the top as apex predators. During the Cretaceous period, the seas saw the appearance of the first true sharks, which evolved into fast, efficient predators. Along with these new sharks, massive schools of fish began to populate the oceans, forming one of the most abundant and diverse marine ecosystems the Earth has ever seen. The seas were dominated by an intricate web of predators and prey, each species filling a specific role within the ecosystem. The extinction of the marine reptiles and the rise of modern oceans. The end of the Cretaceous period, approximately 66 million years ago, marked the end of the age of dinosaurs and marine reptiles. The mass extinction event that wiped out the dinosaurs also led to the disappearance of many marine species, including the iconic ichthyosaurs and mosasaurs. With the disappearance of these marine reptiles, the oceans underwent a significant ecological shift. In the aftermath of the extinction, modern marine ecosystems began to take shape. Mammals, such as whales, dolphins, and seals, became the dominant marine predators, and the oceans saw the rise of fish species that would come to dominate modern ecosystems. Coral reefs continued to grow, and the first seabirds appeared, adapting to life in the open oceans. Today, the oceans are home to an incredible diversity of life, from the smallest plankton to the largest whales. While the prehistoric oceans of the past were very different from the seas we know today, the basic principles of marine ecosystems have remained the same. The oceans continue to support complex food webs and play a critical role in regulating the planet's climate. The impact of prehistoric oceans on today's world. The prehistoric oceans had a profound impact on the planet's atmosphere, climate, and biodiversity. The ocean's ability to absorb carbon dioxide and regulate temperatures helped to stabilize the planet's climate throughout its history. The oceans also served as a cradle for the development of life, providing the conditions necessary for the evolution of diverse ecosystems. Today, the oceans face significant challenges, from rising temperatures to acidification, caused by human activity. Understanding the history of the oceans and their ecosystems can help us better understand the impacts of climate change and how we can work to preserve the health of our planet's oceans for future generations.